Good morning and welcome to today's webinar. My name is Aranza Zugalan and I'm a member of the Build Up editorial board. Build Up is Europe's largest international portal for energy efficiency in buildings. It is a unique community that provides the opportunity to discuss, contribute and collaborate with other experts in this field. Build Up aims to bring together stakeholders working in the building and construction sector to reap the collective intelligence about energy reduction in buildings by encouraging knowledge exchange. Our editorial work is organized around a topic of the month, which allows us to dig deeper into specific themes. Each month, several items are produced by Build Up, such as overview and technical articles, written interviews, and much more. Build Up also offers the opportunity to host webinars on topics related to energy efficiency in buildings. More recently, Build Up has opened its doors to distinguished experts in the field to share their knowledge in front of our cameras in our Build Up expert talks. The Build Up portal shares daily the most relevant events in the field of energy efficiency, but we also participate actively in many European events around the year, such as EPB Center and RIBA conferences, Horizon 2020, Interreg and Cost Action events, Covenant of Mayors, and more, always with the aim of further disseminating the results and helping to create high-quality media content. The Build Up portal is updated daily, reaching around 120 new items each month, including news, events, publications, articles, and video content. But Build Up is not only us. Build Up is a community, and we invite you to be part of it. By becoming a member, you can contribute by uploading your own content and promoting your news, events, case studies, reports, and more. By contributing content, Build Up will help you to reach a broader audience through our online portal, our social media channels, and our monthly newsletter. Visit us at www.buildup.eu to find out more. It is a pleasure for Build Up to host this two-day seminar entitled Microclimate Change and Envelopes, Understanding, Modeling, and Design in Light of a Changing Climate, brought to you by the Urban therCOM project and curated by senior researcher Emanuela Giancola and Professor Emanuele Naboni. This seminar is focused in the relationship between local climatic changes and the design envelopes and will take place over 2 days. In today's agenda, keynote speakers will introduce their work and upcoming challenges related to climate change modeling, coupling of microclimate and building forms, envelopes via computational advanced workflows. The agenda tomorrow will center around matters of decarbonization and energy, health and comfort, ecology, and nature-based solutions. In today's agenda, we will start with an introduction from Emanuela Giancola of Center for Energy, Environmental and Technological Research, CIEMAT, and Professor Emanuele Naboni of University of Palma, Royal Danish Academy, the UNSW in Sydney, UC Berkeley, and ISOS Mario Cucinella. The introduction will be followed by session 1 on modeling linking outdoor and indoor, where we will hear from Michael Bruce of University of Mainz, Victoria López Cabeza of University of Sevilla, Naga Manapragada of Technion of the Israel Institute of Technology. Session 2 will focus on microclimate, form and surfaces, where we will hear from Carmen Galán Marín of University of Sevilla, Miguel Núñez Peiró of Architectural Technical School of Madrid, ETSAM, Agnès Salvati of the Polytechnic University of Catalunya, Massimo Palme of Universidad Técnica Federico Santa Maria in Chile, Francesco De Luca of Tallinn University of Technology, and Angelos Kronis of Infrared. The third and final session of today will center on climate change and modeling, where we will hear from Giandomenico Burro and Salvatore Carlucci of the Cyprus University, Nestoras Antoniou of University of Cyprus, Bahik Nik and Kavan Javanrodi of Lund University, and Alberto Martilli of Center of Energy, Environmental and Technological Research, CIEMAT. Each session will be followed by a brief discussion. We invite the audience to send us questions through the GoToWebinar platform that may be answered during the discussion session. Please specify which presenter your question is for or if it's it for all presenters. We will be able to find the recording of the build-up portal together with the presentation slides from Wednesday of next week, when we will also be launching the brand new build-up portal. So keep an eye out next week to check it out. I now finally hand over to our host and moderator, Emanuela Giancola. Emanuela, the floor is yours. We wish you a very nice workshop. Enjoy.
Okay, thank you, Arantxa. Thank you for the presentation, and thank you to Build Up to be able to host this today webinar. I'm really glad to be there and see how many old friends and meet new ones and friends and colleagues. And for who those didn't know me, I'm Emanuela Giancola. I'm a researcher in the CIMAT, the Research Center for Energy, Environment, Technological Research here in Spain. This webinar is organized in the framework of my national project, Urban therCOM, that is related with the strategy for modeling the urban material for a more livable city. A brief introduction of my center. CIMAT is the National Center, as I already say, for Energy, Environmental and Technology is divided in 5 big departments. I'm part of energy department, and specifically I'm working the energy efficiency in building unit. In the unit, we carried out different activities related with energy and the building environment. We carry out energy simulation, envelope characterization, climatology characterization, and many other that you can see in the screen. And in this activity, I'm leading this project related with the microclimate condition and how the envelope can improve this microclimate at the indoor condition in the building. I have to say that Urban therCOM is part of the big coordinated project, MATEMAD. The MATEMAD starts with the hypothesis that the use of optimizing material can improve or can reduce the effect of the urbanity island in the city. The aim of the project is to generate knowledge about the impact of the urban material in the city and improve the quality of the environmental spaces and the well-being of the person in the city and in the building. The project is, the activities of the project is divided in 3 sub-projects. The first one is leading by Instituto Eduardo Torroja of the National Research Council here in Spain, and they made out a study related with characterization of the urban material. The second sub-project is leading by University of the Architectural Faculty of the Polytechnic University of Madrid. They're leading with the monitoring of the environmental parameters. And then the last one, that is one that I lead, Urban therCOM, related with the modeling part of the project. The project activity are divided in 5 big steps. The first one is related with the assessment of the vulnerability within the city of Madrid, related to the themes, to the topics related with climate change. The second step is related with characterization of thermooptical property of different kind of material, both in situ and in laboratory. The third step is related with the monitoring of the case study that we choose. The fourth one is related with the modeling strategy to be able to model and to simulate both indoor and outdoor comfort. The last one steps is related with the optimization of the results, and in this kind we want to use life cycle assessment methodology, and also this part is leading by CIMAT. At this point of the project, related with the simulation part also, we have already chosen our case studies within Madrid based on the energy poverty index, urban tile intensity, and the morphology of the cities. And the first part related with the vulnerability within the city is carried out by Instituto Eduardo Torroja, and the last part related with the morphology was led by CIEMAT using the homogeneous urban zone methodology. Related to the concrete simulation part, we design a simulation methodology based on Grasshopper digital workflow. At the moment, we are still at the beginning, and we are only made some simulation related with some thermochromic coating in a really simple test room, basically in Madrid, of course. And the further steps related with the integration of the environmental part and the building part and the material in a unique workflow. In this sense, we are here with the help of Emanuele Naboni and his PhD student Marcello Turrini, that are also part of our work teams, and they are helping us to develop this big digital workflow. And from my side, it's all. Thank you again to everyone to be there with us today, and I will really happy and now leave the floor to Emanuele. Thank you.
First of all, thanks to all the speakers that enthusiastically accepted this invitation to share their knowledge. Thanks to Emanuela for involving us in this project. Thanks to Build Up, Arancia Sciences, Emily, and others that are giving us a better structure of this event. Just a brief presentation about myself. I'm active in different countries. Try to merge findings from research to the practice. And this has been laid with several collaboration with William McDonough, SOM, and other entities. At the moment, our work deploys in several parts of the globe, both for research collaboration, but also with a lot of master plan and building design that are encompassing all the findings we are developing about climate change. After this brief presentation, we can now dig into the topics of this workshop. The idea is that the boundaries of climate change are understood, but as reported by the sixth assessment document of the IPCC, what we see as poorly implemented is a technical understanding on how architecture and urban design may be modified in order to incorporate such changes. So the session of today and tomorrow revolves around the topic of linking throughout envelopes, throughout facades, several scales, as we are seeing as more and more a connection between the regional climate change and indoor flows should be managed in an intelligent way. This gives the possibility to structure the conference around 6 macro areas or 6 scales, shifting with some focus at a certain point on how microclimate is modeled, how building form and materials are then featured differently, and also how the indoor may change. This connection between the macro and the micro is what characterizes today. Also, there is a digital background in this workshop, and the idea is to understand how data coming from satellites as well as locally measured can inform a design. We also wanted to give through a final session some outlook, such as rethink the physics of this interaction, including the modeling and understanding and the design of ecological living layer. I don't like so much to call it nature-based solution, but perhaps living layers, it's an interesting definition. The boundaries of this workshop are those of a different climate. These are some example of the tab of the climate tool we are developing with Professor Schiavon and along with Marcello Turrini, where we try to identify for each site the possibility to quickly visualize what are the threat of a different climate, or also what are the opportunities that we are going to face. Thinking about the envelope, what strikes us is that already at low angles, as you can see here in the mid chart, local temperature are quite high. So in a way, the typical rule of thumb of consideration and thinking about season and protection or exposure for passive collection are going to change. Another factor is that the frequency of temperature during the year is changing. This is a chart for the city of Berkeley, where we see that we have much higher number of temperature at higher temperature. This means profound changes, of course, in terms of microclimate. But also, if we think of an indoor space, this chart exemplifies how there is a shift from an acceptable temperature to a hot temperature, as well as there is a shift along the year from a hot temperature to a very hot type of temperature. So this means, in a way, create the need of designing new tension between what happens between the outdoor and what happens between the indoor. Working with different cities or different master plan, and also assessing how climate is changing micro-specifically, what we see is that there is actually this conjunction. So for instance, this is a consultancy for the city of Gothenburg, where we are asked what would be the impact of modify vegetation on site? What if we expand our building stock? What if we want to retrofit just certain type of buildings, or we want to redesign certain part of the city? So this is just one area. This is a very large model where there is a coupling between outdoor and indoor, and also where all living systems are modeled. When we project this model calibrated according to local measurements, when we project it to 2050, we can see how we can experience temperature within certain building of even 40 degrees. Also, we can see how certain areas, as compared to other, are able to have a significant change in their temperature. But also we can see the virtue of certain topography, certain buildings, as well as certain living system of retaining the same temperature in 2022. So common denominator of all your intervention would be to reflect about this thermal resiliency. How can we secure also within the context of climate change the same condition of today? And the second pattern of speculation of your research is about adaptation. How can we use the change in temperature to design new types of building, new type of biodiversity? How can we use these elements? And this is exemplified, for instance, throughout a series of secondary linked type of factor, such as, for instance, air pollution, but this can be pollination or health charts. Tomorrow I will explain much more about the connection between design, envelope design, and secondary type of interferences. Today is only we only want to offer, let's say, an icebreaker. But implication of this understanding, modeling, and design for climate change are various, and we are going definitely towards an interdisciplinary type of design. So we are very happy to have some presenter that trying to find this secondary rate type of implication of a changing climate. When we look at the building, also we can see throughout heat flows for a typical day in summer, how for this site there are certain buildings like this in red that basically do not have this exchange with the variation of the exterior microclimate, whereas we have certain type of buildings that, especially during night, this is the second part of the day, are able to dissipate a significant amount of energy. And just to chase or provoke a bit, what we can see is that the building that may adapt the best to climate change are those designed before the passive mantra design mantra was established, as they have a major possibility of dissipate during night. So this is a provocation, and let's see how this is received from the different type of speakers. We change now scale, and I want to show some example where I try to design for climate change, operating in conjunction with some architects. This is a building designed 3 or 4 years ago. And the idea of the envelope is the one of understanding climate change and try to play with it, not creating a barrier between the indoor and the outdoor, but it's the facade by having elements that reflect shortwave in different direction, create a variety of interior condition where energy is filtered and interpreted. The second design, it's the Lavazza headquarters, where the idea is to create envelopes that are able to create different interior conditions by an array of thrown-by wall, double skin facade, spandrels of different color, glaze of different colors, layering of glasses on different planes. This is very interesting, as from one side it contributes to a variation of the interior. Also, it contributes to the outer microclimate by creating a different microclimate on the outdoor, and I will show this in a second. Another project, a consultancy, where the idea is to take the forces from the outside and try to relate to the scale of the human body throughout perforation at different parts, as well as vision area of different geometry, so that the relation between indoor and outdoor is going to be interpreted. These are studies that support this type of designer choices. What we can see is that, if you can follow my mouse, by changing type of envelope, what we are going to influence is the outdoor. For instance, in a canyon, in a plaza, we can see how mean temperature is very much affected by the envelope, as well as the happenings that we have within the space. Potentially, with certain design, we are able to control emissivity and reflectivity, and this is perhaps most of the research I'm conducting now in Sydney with Professor Santamuris. We are able to actually modify condition on different scale. Further research showed us that just by changing simple properties of the envelope, we are able to influence indoor-outdoor temperature by up to 4 degrees, if you can look at the right chart. And a strong emphasis in this workshop, it's as well as in design, on the computation methods that are behind. So we have now developed by some of the presenter interesting workflow that allows us to branch all the physical happenings for mostly and it's a very interesting phase where we are able to assemble different scripts and understand a physical problem and understand how our design is able to have this double impact on the indoor and the outdoor. We just finished, along with Emanuela and Marcello Turrini, a workshop of a few days where we had a very interesting array of students, expert students from ICOM and different practitioners from Europe, as well as different universities. And all of them were then able to design different type of envelopes and understand almost in real time the implication on the energy demand for the building, the indoor comfort, as well as design for the outdoor. So tomorrow then it will finish with some session about living system. What we are trying to do, especially in Copenhagen, is try to understand how the thermodynamic of the envelopes can support a new layer. For instance, this in Alaska, try to use permafrost melting to collect some bacteria that create some system able to purify air as well as to produce food. And the thermodynamic basis needs to be very strong to achieve this type of performance. Also very interesting, the idea of involved flows that are related to the culture of a place like this in the Faroe Island, where together with a student, Jonathan, the idea is to use fish that are going to be dry, that are drying throughout this facility as an element that modify the hygroscopic condition within a space. And we have several experiments of this kind, and it's probably quite interesting to begin to understand how physics can inform more cultural and natural values. Perhaps this is well summed up in this diagram that was made by a student of ours some years ago, which I found is very interesting. We are probably, when coping climate change, needs to think of abandoning this type of model on the left, where there is this separation through the envelope, where we have basically an outdoor and indoor that are highly separated and distinct, towards going through this major relation between indoor and outdoor, where the ecological layer enters into the building, where this thermodynamic transition is variable and dynamic. So the overall background of the workshop is also the one of shifting from a sustainable paradigm, which is mainly related to the idea of mitigating, limiting the impact of climate change or make them neutral, whereas the idea is to interpret climate change as an opportunity to adapt, as a way to regenerate, as a way to create facade solutions that are not apart from nature, but they are part of nature. Needless to say, we need evidence-based and computation to achieve such type of targets. Yeah, to conclude, and we are miraculously on time, you may find some background to this topic in this book, which is free for download on ResearchGate. Now it begins to have some years, perhaps almost 3 years, so it's time for a new publication. And for those that want to be in touch, perhaps via Instagram, I suggest to look at this page where we try to put some architectural work, and it's Emanuele_Naboni_climate. So it's probably time to get into the depth. Me and Emanuela will try to moderate the sessions, also in coordination with and through the help of Arantxa and Emily, but we thanks very much for all the support in preparation and in execution. So perhaps I leave the word to Emanuela to coordinate this session.
Okay, so we start the first session with the presentation of Michael Bruce. If Michael is...
Yeah, thank you very much, Emanuele, for inviting me to this fantastic webinar. So hello, everybody. So being on a guy from the outside, so probably I have to stand a while and think about the inside. Well, maybe some of you come from the other way, so they mostly think of the inside and they have to think about the outside. So I'm just thinking today I would give you just a very brief idea of what we are thinking at the moment. How can we link these two parts? Because obviously we have just seen it. We cannot see these things separately. The building is not isolated, and also the outdoor environment is not isolated from the buildings and the surroundings. But obviously at the same time, we cannot model everything on the same level of detail we want to have. So we cannot model the inside of a building with all its components like lights, people, computers, heatings, and so on. So whatever is inside a building, and at the same time model the outdoor environment with a high resolution with buildings and other buildings, trees, water elements, and so on. So there has to be a compromise. So the one thing, obviously, in terms of modeling microclimate conditions, both in the inside and the outside, is of course to define the interface between the two. So this is just an idea picture. So what we can do with microclimate models, so models which are designed for the outdoor space, so they can of course simulate parts of the building, like the facade temperature, the energy transport into the inside, depending on what kind of facade material has been used. Of course, depending on the microclimatology conditions at the facade, the wind speed, the turbulence, the air temperature that is transported into close to the building. But at the moment, we have to stop at that point. So we cannot say open a window and let the wind blow into the building. So it's technically possible, but it really would blast the model's capacity and the capacity of the computers that we have available at the time being. So when we think about modeling, we also have to think about the practicality of modeling. So it's easy to build a huge model that has everything inside of it, but in the end, nobody can use it, or you need a supercomputer to handle that. So that doesn't bring us much of benefit except being in a scientific paper research competition. So I think these things are pretty obvious, and we can, it's just the same principle, it's just with showing the facade elements. So, but I picked two other aspects. So for we ask for projects or what we are thinking about architecture, we have often the problem that we have ambitious spaces, so that we are transition spaces. So it was not right clear, is it an indoor space or is it an outdoor space? It has both characteristics of an outdoor space, but it has at the same time is largely influenced by building materials or urban elements materials, just for example, a football stadium. So inside that stadium, we are somewhere in between indoor space and an outdoor space. So that means to evaluate the conditions, the microclimate conditions that actually take place, for example, inside such a soccer stadium, we have to use both approaches. We have to use approaches from building physics on the one side, and we have to use approaches from the metrology parts, the boundary layer metrology, to solve it. And in the final result will be a mixture between the two. So nobody can say at the beginning how many percentage will be indoor characteristics, how many percentage will be outdoor characteristics. So we obviously do not need to say this at the beginning, because we have the possibility to model this. Or another example, when you say, okay, it's a football stadium, is okay, I'm not interested in football, so I don't care. But of course, any building or most of the buildings do have these transition spaces, maybe a terrace, an indoor opening, an atrium, or whatever you can think of. So this, for example, is the office of the foreign exchange embassy in Berlin. And we also see in a more or less classical building these spaces that actually behave like a transition space. And this is where we are working at the moment to enable our microclimate models designed basically for outdoor spaces to understand these transition spaces without transforming themselves to be a building energy model. Or another aspect, which I think is quite crucial and has not been handled very much because it's not really climatology, but it depends, because when we talk about green infrastructure, we talk about the value of properties. It's also the question, what do we see from the outside? So what do we see from the outside, from the inside building? So what is the window view? Green infrastructure is nice if we are outside seeing this infrastructure, but we have to consider that most of the time, at least in our countries where most of us came from, we are inside the building. And so infrastructure also needs to work maybe from the inside view. Means it's good if I know how much fraction of green space do I see if I look out of my window, especially when thinking of classical windows which do not span over the complete facade. So this is also a very interesting analysis point of view, maybe a bit outside the climate aspect. but we are in a holistic approach, so we have to consider everything. We cannot just look at the microclimate. We have also look to say what is the impact on rainwater drainage, what is the effect of traffic flows, and so on. So to provide a realistic redesign or a realistic idea of climate change mitigation, all these aspects have to be considered. Even we are climatologists from our profession, we cannot just start designing something and then came up in the architectural process or in the community process and see this doesn't simply work because there are trees where cars need to go or other things. Yeah, the second thing we're interested in, and we are also going to introduce a very first version now in the next release from Envimet. So no advertising, just to give you the idea why we are working at it. So when we talk about the outside, especially in urban areas, we have to think about walking in this urban environment. All these thermal comfort maps you see most of the time, it doesn't matter if it is UTCI, SET, PET, or just name it. All these are static indices. We should not forget these. All these colorful maps are always assuming that you're on the same location for a long enough time that your body energy balance is balanced. And that means in an outer space in the summertime, it takes 20 to 30 minutes, depending on where you come from, until this UTCI or PET is actually reached. Before these 30 minutes, 20 minutes, your skin is not that hot. So that means if you are there at this location, your PET will not be the PET which is shown in that map. And saying when you come from the inside and it's climatized, it has an indoor temperature of say 15 degrees or 20 degrees, and you pop into the outside world, and we ask ourselves, is our outer environment comfortable? We have to consider our thermal history. So, for example, this walk here from in Manhattan, from Battery Park, which is here just in the west, down to the direction Brooklyn Bridge over the waterfront pier. And this is the skin temperature I have just plotted. And obviously, starting here with the cool skin temperature, it takes time to develop if it's going hotter, if it's going cooler. And we need to have these transition processes also in the consideration of thermal comfort, because walking through an environment, my perception, my thermal perception of an environment in which I walk is depending on what are the changes in my energy balance. This is something that I recognize. Is my energy balance dropping or is it rising? This is even more important than the question, what will be my final skin temperature if I stand in Battery Park for 30 minutes? And to do this, we need different methodologies. So we need to follow the pedestrians, we need to follow the biometrology processes that take place at our skin, depending on the microclimate, the wind conditions, the solar radiation, and so on, where we are at the moment and how long we are. So this is something, this is also linked not only to the outer environment, but also to the indoor environment when thinking about leaving a climatized space, walking through a non-climatized outer environment and back to a climatized space, for example. So that's something we are working at the moment, and I think my 10 minutes or whatever I had are over. And yeah, thank you very much.
Okay, thank you, Bruce, Michael, really interesting. And the next speaker is Victoria Lopez Cabeza from the University of Sevilla. So Victoria, the floor is yours.
Thank you very much. Can you hear me?
Yes, perfect.
Okay, thank you. So yes, my name is Victoria and I'm from University of Seville. And thank you very much to Professor Naboni and also Emanuela for inviting me today. Here to show some of the work we have developed in the research group TEP 206 in the architectural school. Also during my PhD thesis when I worked in these 3 research projects already finished. The 2 first ones are trying to analyze and simulate the microclimate of small outdoor spaces in buildings like courtyards, and the third one applying the learnings of these other 2 projects to the design of the solar decathlon competition for the 2019 in Hungary. So why are we analyzing courtyards? Because they are known to be key elements in the passive conditioning of buildings, especially in hot and dry climates, like the Mediterranean climate in where we are. And they are present in many traditional buildings in courtyard all around the world. We have developed monitoring that prove that they have a tempering effect. They can mitigate extreme temperature that when it is very hot in the outside. But this performance depends on many parameters, not only the geometry of the courtyard, but also if they have vegetation of water elements, the characteristic of the materials, shading devices, etc. We have performed many monitoring campaigns. For example, in this study, we analyzed up to 20 courtyards in the Mediterranean climate in different cities, and all of them achieved a tempering performance. I mean, they were able to have a thermal gap, or the difference between the outdoor temperature and the courtyard temperature, up to 10 degrees. But the performance was different in up to 8.5 degrees between some of them. The best performance were achieved by the deepest courtyard during the day, but during the night they had some overheating also effect. We have also analyzed courtyard thermal comfort inside the courtyard, and because of this unique characteristic of the space, which is not completely outdoors, but it's also not an indoor space, we have applied different standards and indexes, and we have compared the results between them in this study. For example, on the bottom of the presentation, you can see new results also contrasting UTCI and PET with the adaptive comfort model. However, my PhD thesis was focused on the simulation of these spaces, because we know that the thermodynamic effects inside the courtyard produce this stratification and this lower temperature in the lower levels. But when we simulate them with traditional tools, they consider that the courtyard temperature is the same as at the outside, and this is not true. And this is a problem because we cannot account for the benefit of these spaces. We perform some simulation and some studies to quantify this effect. For example, in this one, in collaboration with Jesus Lizana, who is presenting tomorrow too, we simulated a building with a courtyard using different outdoor temperatures, the typical year, the rural weather file, a local climate zone outdoor condition monitored by us, and also considering or not the courtyard. And we found important difference in the number of discomfort hours that we achieved. If we only consider the local climate zone, there was the highest number of discomfort hours, but considering the courtyard microclimate, we could reduce especially the extreme discomfort hours in an important way. So the consideration of the courtyard is important. This is another study, in this case using the tool that the Spanish government provide for the energy certifications of buildings. And we also measure the reduction in the energy demand with a percentage different up to 10% at the lower levels, where the courtyard has the lowest temperatures. We also extrapolated the potential of the courtyard at the city scale, using the cooling degree days methodology to quantify how the potential of using a shading strategy in courtyards in a city like Cordoba, where this city is the one with the highest amount of courtyards in Spain, and that the reduction could be up to 30% in energy demand in 69% of the urban plots. But this is all about monitoring, and we want to focus on the simulation of the courtyard. So we have tried different tools in this study. This is an old study from 5 years ago using MBMet, and we found that the software was able to simulate the tempering effect, but not in such high accuracy as we would have wanted. I know that with these new releases, probably these results are going to be better. But we also tried other hybrid workflows or using the Ladybug tools with the CFD plugin that they have, the Butterfly plugin. And using this workflow, we monitored we simulated the performance of different courtyards, and we were able to achieve faster results and more accurate results. Using that workflow, we analyzed different strategies to improve the performance of the courtyard. For example, in this case study, we simulated a courtyard with and without a shading device, and we achieved an important improvement in the UTCI index in the courtyard, especially when the sun was high, with a larger area at lower levels of UTCI. We also simulated the effect of thermal inertia and ventilation in the solar decadon prototype for the European competition. In this case, we simulated 3 different levels of thermal inertia in the walls, from almost zero inertia with a PVC canvas that it is what was built, and then with 2 traditional walls in the courtyard. And we found that if the courtyard is closed with no ventilation, the highest the thermal inertia, the better the results at the time when the temperature is higher during the day. But also during the night, it had an overheating effect. But if we open the courtyard, the ventilation and the outdoor air that is coming in is making more or less the results from all the walls, which means that we can combine thermal inertia with ventilation in order to optimize the results. Finally, I'm going to show you some coupling tests that we have done using the building energy simulation tool that Spain provides in order to make this methodology accessible to professionals with the simulation of the courtyard, coupling the Ladybug workflow with the Hulk tool. This has been done in the Grasshopper, Rhinoceros and Grasshopper interface, and with some blocks of Python code in order to link first the geometry of the building to being able to export it easily, and then to analyze the climate to find when are the times that we want to simulate the courtyard, because we need to reduce the CFD time for the simulation in order to couple the time between one tool and the other. And then we simulate the courtyard and we export the courtyard temperature using a Python code to generate all the files that the software needs to change the boundary conditions of the elements that are facing the courtyard. And these are some of the preliminary results of this test that we have done, where you can see that the temperature in the rooms facing the courtyard changes a lot when we consider the benefit of the courtyard. Also, the energy transmitted by the walls and the windows facing the courtyard changes in a huge proportion. So just to conclude, we find that the microclimates generated in the outdoor spaces of buildings like these courtyards influence in an important way the energy demand and the thermal comfort of users. And we need to design and test different simulation workflows in order to account for their benefit. We are also working on the accessibility of the professional sector to these methodologies in order to promote the climate change adaptation of the built environment. And well, I have showed you some CFD and BS hybrid simulation workflow. We are still working on that, but we could account or quantify the benefit of the microclimate of the courtyard. And we have some future works, but Professor Carmen Galan is going to show you later some of the ongoing projects that we already have. Thank you very much. If you have questions, that is my email. Thank you.
Okay, thank you, Victoria. And then we leave the floor to Naga. Thank you, Naga.
Yeah, hi. Hello, everyone. I'm Naga, PhD scholar in Environmental Performance and Design Lab at Technion Israel Institute of Technology. Since October of 2022, I have been working on the topic Urban Microclimate Integrated Building Energy Modeling, supervised by Professor Jonathan Nathaniel. Today, I'm here to discuss my perspective on how integrated simulation is neither simple nor complex with available know-how. So in this presentation, I would like to answer the questions: why is integrated simulation required? What are the methods available for integration? And how are integration approaches neither simple or nor complex? So we all know that cities have major stake in world energy consumption, of which 30% accounts for building operational energy use. As most energy generation is fossil fuel reliant, the reports on rapid urbanization and global warming are raising concerns about future greenhouse gas emissions. All thanks to building energy modeling tools that are allowing the designers to make informed decisions pertaining to building geometry, envelope, appliances, equipment, and automation controls that promote energy conservation, renewable energy generation without compromising the visual and thermal comfort criteria using the typical climatic conditions. So beyond building energy conservation measures, we have also urban and landscape design measures that can impact the microclimate and improve the building energy performance. But by default, the building energy modeling tools are not equipped to account for dynamic microclimatic conditions surrounding the subject building or buildings. It is no more a hypothesis that microclimate impacts on building energy performance. A recent review by Lozet and his colleagues have discovered a deviation in heating energy load between 15% and 89%, and also difference in cooling energy load between 131% to 200% for not accounting for the urban climate and context. From these findings, we can infer that urban microclimate integrated building energy modeling is important for recognizing potential urban and landscape design measures, and also for accurately assessing the urban buildings energy performance. After an extensive literature review, we have classified the integration approaches into two based on the microclimate data used for simulation. So what are these representative and surface specific data methods, and how do they differ? In a representative data-based approach, the point in location or averaged urban microclimate data, either generated either from monitoring or from urban climate model simulation, and are replaced in weather files used for building energy simulation. But this method raises serious scientific questions like which point or points data represent the microclimate surrounding the building. So can the representative data in weather file help the building energy modeling tools account for varying heat flux around the building? So to get this answers, to get answers to these questions, we need to take a few steps back and understand the building heat transfer mechanism in urban context. Yeah. So we all know that convection, radiation, and discharge are three key modes of heat transfer in buildings. Discharge heat transfer includes air-to-air heat transfer between indoors and outdoors through ventilation and infiltration. So according to previous studies, wind speed changes with building and contextual urban form. In the case of radiative heat transfer, the surrounding urban surfaces exchange long wave radiation with building surfaces. Finally, the convective heat transfer, which is heat exchange between the ambient air and the building envelope, is a function of near surface wind speed, air temperature, and the building surface temperature. But here, we need to realize that the building surface temperature is affected by radiative heat transfer, while the near surface wind speed and air temperature are impacted by the contextual urban form, as mentioned before. Therefore, the holistic building heat transfer with contextual environment is technically surface specific, but not representative. And now, many of you might ask, do building energy modeling tools completely ignore near surface climate impacts while computing heat transfer? Almost all the building energy modeling tools that use single weather files for building energy simulations compute the heat transfer based on few assumptions. For example, here, Energy Plus accounts for the long wave radiation exchange by assuming that ground surface temperature equivalent to the air temperature. But the ground may be paved with concrete, bitumen, or grass in urban context. Now, theoretically speaking, can the surface temperature be equal to air temperature? So in the case of local outdoor air temperature, a constant gradient is used to compute height-wise air temperature from the dry bulb temperature in a typical weather file. So similarly, even wind speed for a specific altitude is also extrapolated from a representative climate data point. In an urban environment, a microclimate is highly variable, not just with height, but also based on the point in location. That is what even Professor Bruce has discussed before. So surface-specific microclimate data makes more scientific sense. The urban climate modeling tools are integrated with building energy modeling tools in various methods where climate variables and heat transfer coefficients are computed, then transferred to the building energy model at each step of simulation. So this kind of integrated co-simulation of urban climate models along with building energy modeling tools are termed as coupling or chaining, which even Victoria has discussed in her presentation. As listed here, several setbacks exist in available chaining and coupling approaches. But the most important limitations are the computational expensiveness of CFD-based urban climate models and the programming knowledge to co-simulate tools. Even in Victoria, one of the research where coupling approach has been showed by Victoria, she has used new components to couple the two tools. These two make the urban microclimate integrated building energy modeling tools complex for traditional building designers, novice to CFD and programming, but simple for designers with both expertise. So therefore, we at EPDL are developing an ML-based urban microclimate integrated building energy modeling approach, currently only for Mediterranean climate of Tel Aviv, that can harmonize building level, urban morphology, and landscape design parameters in annual simulations. The novelty of our research will be two-way coupling. That means the data of surface temperatures are generated from the detailed building energy simulation tools, not just depending upon the CFD-based urban climate models, and also an explainable machine learning model development where both correlation and causation between input and outputs are justified. The framework for developing ML-based microclimate models shall be replicable to generate region-specific models in future. We are trying to ensure that workflow is user-friendly for all urban and building designers. So thank you so much. I'm happy to accept any suggestions, recommendations, and remarks on this topic. Thank you, Professor Emanuele and Emanuele, for this opportunity. Thank you all for your time.
So, thank you so much, Naga. So we have had a very interesting first session. To make a resume, Michael, Bruce spoke and introduced the topic of create this important design tension between the climate balance as well as the energy balance, as well as people physiological type of balance. And this type of positive tension was then taken by Victoria, who discussed specifically how a typical typology as the courtyard may vary its performance according to geometrical factor as well as envelope factors. And also discussing this outdoor room, which is anyway an inner room in respect to the city, is linked to the very indoor space of the building that wraps the courtyard. And this tension was said to be understudied. So some of that research that of course involves the envelope was considered. Then Naga brought several good points on how this integration between what happens within the building in terms of energy balance and therefore comfort, how this is studied with conventional energy tools such as Energy Plus, where not having a proper modeling of the outdoor and its influence on the indoor may mislead in terms of data. And it was very significant, these numbers that was stating that according to his reference, that not accounting for the correct forces that come from the environment may lead to an error in the energy speculation that ranges from 15 to 89%. So that's definitely a gap. Was very interesting because all the three presentations showed potential and current works, as well as exemplified some sort of gaps. And this left the floor to several questions that were filtered while you were sharing different type of consideration. And perhaps we can have some specific question, and Emanuela will transfer some.
Yeah, and I asked the speaker if you want to open your camera. Maybe it's good for the discussion session.
Yes, please, Michael, Victoria, also to open your chat.
So I have just one question for Michael from my side. It's related to the slide in which you show the walk of the people. How do you simulate the walking trajectory of the people?
Yeah, at the moment, it's some handwork. So you put in points of interest in your model area, and you just generate walks. So you say connect the points, walk from Battery Park over the Esplanade to Brooklyn Bridge. So, but this, just for this very first stage, we also have a different software which is called BotWorld. We are going to have to refactor that because it's actually a bit old. This is based on multi-agent simulation, so that the trip generation is done by artificial intelligence. So the agents find their routes automatically, depending on frequency data. So there's the bus stop, there is a shop, there is, I don't know, an ice cafe or whatever, and then walk. But this can, of course, get very complex very soon, because when you have thousands of agents running and one from one direction, the other in the other direction, it's hard to interpret. So sometimes you have a map and it's hard to understand the map. So sometimes you see hotspots in a map and you say, oh, there is a problem. it doesn't matter if you run from the right to the left or from the left to the right or from the up or the down, there's always a problem. So you have to look for that. But of course, what you do not see are problems which are occurring on a specific sequence of walks. So maybe walk from Battery Park along the seaside up to Brooklyn Bridge, then there may be a sequence of climbing which is very uncomfortable, maybe because you have sweated on some corners, and then you go into a region where strong winds, and you suddenly your sweat is disappearing, you're feeling chilly, and so on. So actually, we need both. We need the multi-agents to have the classical maps, the classical 2D maps we all understand, but we also have, if we look for certain routes, for certain behavior, for certain experiences in the environment, then that we follow a specific person to understand what happens with this person entering here, leaving there, visiting there, to know what are the options to improve it. Because sometimes, for example, for this waterfront example in New York City, when you're redesigning the waterfront with shading elements, with different materials, it's very clear where you have to walk. You walk from the left to the right, or you walk from the left from the other direction. So there's no other way to do it. You kind of walk over the water, and you probably don't walk below Brooklyn Bridge. So this is pretty straightforward. So I think both tools are relevant in the planning process. And at the first step, we have this more simple tool. You have one agent, you have one route, or several. You can have 20 routes if you're busy, and then analyze what happens there.
Okay, thank you. Really interesting, I think.
Yeah.
And
Thanks.
now we have a question for Victoria from the audience. So did the study also consider cross-ventilation of building and its potential impact on the country air's tempering effect?
Well, I showed many different studies, and most of them we didn't consider that. But for example, in the case of the solar decathlon building, we consider that, but in a very simple way. I know that that is an important question, especially if we ventilate through the courtyard. We are changing then the microclimate of the courtyard. We take too much wind or too much air. So everything is connected, and that is something that we want to further analyze. But I know that there is something important. At the moment, we are considering that the courtyard is just like closed, and the ventilation is minimum through the indoors. I don't know if that answers the question completely, but yeah, it's something ongoing.
I hope so, because it's from the audience, so it's quite difficult.
Okay, thank you.
So the next one is for Naga, and the audience said, from my experience, simulated outdoor urban temperature are very different from monitored ones. What is the best method practice to reach similar results that can be used for further work on the building design? So I think you want to say, how do you reach this correct result for the simulated one and the monitored one?
Yes. So this was the same question a lot of my PhD committee also had, is how do you validate the model? So currently we have only considering the base case. So you bring the model, which is the context in like using NVMet. Firstly, it's always better to use simulation tools, but you need monitoring to validate the simulation model, urban climate model specific. Why? Because first, you can't, as I mentioned, like surface specific data is required for the accurate simulation. So to get surface specific, you can't now put all the sensors across the whole urban environment surrounding the building. So this is quite complex. So what we usually prefer is first we take the model, we use NVMet or other CFD-based climate modeling tools, and then we simulate. But for the base case, we validate with the measurement, like a probe or 2 or 3 probes surrounding the building. We validate the model. Then we conclude that, okay, this urban climate model is validated. Then we use it for different scenarios, and then we can couple it with the energy simulation. So we can get the surface specific data. I hope it covers the question.
Yes, it answered the question, and we would like to thank you. We found logical links between your researches. So now we have a break of about half an hour, and we meet for the session number 2 at 12:40. This is going to be an intense session. We have 5 speakers. We have Carmen Galan, we have Miguel Núñez Peiro, Angel Salvati, Massimo Palme, Francesco De Luca, and Angelo Cronis. So we have a good break before so much knowledge. Meanwhile, thanks for our kind and super interesting speaker. See you at 12:40.
Thank you.
Thank you so much.
En inglés igual. Sí.
Okay, welcome back. The break was intended so that you're ready for a continuous session from now on. The topic of the session is related to a set of studies that encompass consideration on microclimate for an envelope and ground surfaces. We have the following speaker, Carmen Galamarin, Miguel Núñez Beiro, Agnese Salvati, Massimo Palme, Francesco De Luca, Angelo Cronis. Not to take time out of the presentation, we introduce the first speaker, and namely is the floor is of Carmen Galamarin from University of Seville.
Okay. Carmen, are you able to?
You are on mute at the moment, Carmen.
Yeah.
Now?
Now we can hear you.
Can you hear me now? Yeah. Yeah, and I can see the slides too. Yes. So thank you, Emanuela and Emanuele, for inviting me to be with you here today. And you asked me to explain about the ongoing projects that we are developing on urban microclimate in a research group. I am professor in the Faculty of Architecture in the University of Seville. And for any of you who want to contact or have any further doubts, you have my email down there on the right. So we are a rather small research group whose name is Sustainability in Architecture, Technology and Heritage, and based mainly in the Faculty of Architecture. As I told you, in the University of Seville, that means being here in the south of Spain, where there are very high temperatures year after year, and they're becoming extreme. Like we are now, for those who are far, we are now in the middle of a heat wave, which is very surprisingly very unusual to have a heat wave in April, which is supposed to be spring, and now the temperatures are here are around 38, so possibly we will reach 40 degrees today, between today and tomorrow. So the situation is becoming very serious, and not only because the temperatures are high, but also because of the risk of the population due to the increase of these high temperatures and there are more and more frequent heat waves. So you can see here in this area, we are in an extreme risk of heat waves. Now, in the research group, we are focusing in projects that could face this type of events. And the first one, which is REACT, is financed by the Ministry of Science in Spain and also by European Union Next Generation funds. And it's benchmarking urban morphology by reviewing adaptive comfort and thermal stress. This project is a coordinated one with Utica. As Emanuele explained at the beginning, this is a way of doing national projects here in Spain. And Utica is basically a group of mathematicians from the University of Valencia, which is a machine learning based forecasting model for integrated assessment of thermal resilience using urban thermal comfort algorithms. So the idea is that we have now, not at the moment, an harmonized outdoor thermal comfort index, because the most frequent ones do not consider the subjective perception of comfort. So they do not adequately describe the perception of comfort for the users, because it's a complex system. So there is no global tool for the moment to assess thermal comfort. And as a consequence, it's not possible to optimize thermal resilience conditions. And it's not possible to discriminate thermal comfort ranges for the population segments who are more sensitive to thermal stress. Also, cross-analysis cannot be performed to determine specific comfort conditions due to one or more population segments. And as a consequence, urban interventions made by architects to improve climate resilience are following at this moment partial or even wrong guidelines. So the idea is to join on one side microclimatic components, as has been already mentioned: solar radiation, mean radiant temperature, air temperature, wind velocity, relative humidity, the ones that are already included in ETCI or PIT, plus the urban components like geometry, orientation, albedo, reflectance, and vegetation, and personal components like gender, age, health, expectation, experience, the possibility of choice, or even the time of exposition, as has already been mentioned by Michael in the first presentation, into an integrated outdoor thermal comfort algorithm that could be shown as a GIS-based integrated visualization tool. So the project aims to improve urban thermal resilience in this context of climate change, developing machine learning-based models that allow to accurately predict the subjective perception of comfort and the interactions with the climate and built environment in order to generate better intervention strategies oriented to adaptation and improvement of outdoor public spaces. Also, including this sub-project 2, the one of the mathematicians, we will use topological data analysis for all the data input and management, and it will allow the optimization of the model evaluation algorithms. Besides, we have another project, which is Mau House, focusing in a multi-scale assessment of urban heat island applied to urban suburbs. And when we mean suburbs, we are talking about the neighborhoods which were fully developed in Spain, basically around the 50s, 60s, 70s, but very similar to those who are in Europe, rather low building construction quality, and population that has severe problems. So this is a project also financed by the Ministry of Science and also by further funds. And the aim is to contribute to the climate adaptation challenges of our cities from a multi-scale, comprehensive, and innovative approach. So we want to promote public policies capable of identifying risk areas and incorporating proposals that guarantee the resilience of the city to the effects of climate change. Also, being able to contrast technical and social viability of these proposals. The proposal is, from one side, holistic, hybrid, and multi-scale, because the perspective contemplates the dimension of the problem from a quantitative and also from a qualitative approach. So we want to identify public spaces that have a high viability of climate adequacy within the cities, spaces of opportunity that we will name urban cool islands that can serve both as climate and social laboratories, and have to incorporate new evaluation mechanisms that facilitate the identification of strategies. In this project, at the moment, we're evaluating 2 cities, Seville and Valencia, and from the point of view not only of architecture, but also, for example, sociologists are also included in this project. So we want to systematize the instrumental nature of the results of the study, and we want to materialize them in tools that help decision makers in the field, I mean the administration. So we have kind of 4 different levels for the objectives. We want to value the importance at city level, the importance of the urban porosity, the urban configuration, like Victoria explained before, for example, in the case of Cordoba with the cordials, analyzing and contextualization in the climate, so that to be able to determine a priority zoning and so obtain case studies. And we also will evaluate urban heat island. I mean, we will focus on the microclimate in the selected cities, determining the possibilities of mitigation of excess urban heat, both at micro and meso scale, and considering the characteristics of the macro scale. So we're using remote sensing systems, aerial thermography, or conventional thermography, meteorological stations, I mean the official ones, and in situ located, and also all type of field work that will be used to validate further simulation results. And also on the citizen level, we want to identify the impact of the climate on public space on the citizens, defining the concept of vulnerability, both social, functional, and with thermal comfort studies. And then the management level, we want to develop decision support tools that facilitate the choice of effective and viable proposals at urban scale that mitigate the risk of overheating. So we will both generate guides for the identification of priority areas and tools that will be based or totally or at least partially in machine learning. So the methodology tries to face all these four sides of the problem. Sorry?
We're very sorry, the time is finished. We will perhaps we can continue later into the session of discussion. Thank you so much, super interesting. We are aware that there is so much more to share, but perhaps we can use the space for the discussion later.
Okay.
Thank you, and we pass to the next speaker, who is Miguel Núñez Peiro from Polytechnic University of Madrid. Thank you, Carmen, so much.
Thank you, Emanuele.
Perhaps we ask.
Hello. Yeah.
Yes. Yes.
Thanks.
Hello. So, well, what I'm going to be talking today. Well, first of all, let me present myself again. I'm Miguel Núñez. I'm from Universidad Politécnica de Madrid. I'm a postdoctoral research fellow here, and I'm going to talk about our recent experience on the creation of a set of urban weather files from a monitoring campaign. So let's see, why focusing on, or why do we focus on the urban weather files, on the weather files themselves? Well, we think there is a clear need to facilitate or increase the use of the urban climatic information among all stakeholders. So I think right now it's quite centered in the research community, and there have been some efforts such as this type of tools like the urban weather generator that have done, well, important efforts in order to increase that outreach of these type of models, of this type of climatic information. But I think we have to still do many more efforts in that line. So we think that since this is critical like extending the use of these weather files, we decided to focus on creating a set of weather files representing the whole situation of the municipality of Madrid as a pilot, as a test, in order to check if this process could be replicated in other areas. To this respect, instead of following the modeling approach based on numerical morphing, sort of saying, so instead of focusing on the modeling of the physical phenomena of the environment, we decided to follow empirical morphing. So forgetting somehow about the physical phenomena that was taking place, forgetting a little bit about the energy balance, etc., and focusing more in the inputs and the outputs, focusing on the inputs that we have, the boundary conditions that we have, and which outputs we were getting in the city, and take advantage of the power that we have nowadays with artificial intelligence, with empirical modeling, in order to pursue that objective of creating weather files. We focused basically on empirical morphing because, well, we think that it's increasing. We have more and better access to data nowadays, so we have not just information that we collect from the networks that we deploy, but also we have a lot of information anytime, like every day, with more accuracy, both with more definition, both in the spatial and temporal scales. We have also much more access to land-based networks. We have improved the provision of metadata to better contextualize the data that we collect at the urban locations. We have also more information to determine correctly the source area of these measurement points and determine if they are representative or not of that urban environment, improve quality assessment, improve quality controls beyond the World Meteorological Organization recommendation, specifically for citizen weather stations. And at the end, we have more and better modeling tools. Right now, there is like this hype about artificial intelligence, like in the last year or so, right, or the last months. But if on the background, we can see that in the last 20 years, it has been being integrated into the urban climate modeling, and that every year gets much better. And there are like we have moved from this numeric empirical modeling based on multivariate correlations, and we have moved to artificial neural networks, to transformers, and to other type of modeling techniques that are being more accurate and are increasing or facilitating the labor of modeling in an empirical way. So to test this process, what we designed was this workflow from the very beginning of the monitoring and the contextualization of the measurements to the analysis of that data in order to identify trends and other patterns, to the creation of the urban weather files. For that purpose, the core, as I was saying, was the modeling of that of these artificial neural networks that we were using for morphing the time series that we have from a reference point. So in other words, what we are doing is training a model with limited data, with about 1 year of data, of climatic data, in order to learn how to morph longer data sets, and therefore be able to select or to extract a representative meteorological year, right? A typical meteorological year out of that longer time series. So to summarize a little bit what we did a couple of measurement campaigns. One focused on the spatial distribution of the urban heat island, through which we were able to identify the hotspots and the cold spots in the city. And then thanks to that, deploy a fixed network of sensors across the city that were measuring and gathering data, temperature, and relative humidity data through a couple years on an hourly basis. With that information, analyzing it, graphically and of course statistically, we got to get some insights on the urban heat island of Madrid, confirm some of the previous trends that were highlighted by other colleagues. Also highlight other patterns that we found out, such as the absence of a strong seasonality on the maximum and minimum daily intensities, and with that information, carry out the modeling of the conditions for each one of the measuring points. This is an example for the point located in the city center. You can see in black line and in the dotted line the prediction following two different approaches that we were testing, but overall both approaches were quite good in a context of standard data availability to get to predict the measured temperature, or get to not predict, to model the measured temperature at that urban location in many different scenarios, both with strong heat islands and almost no heat island at all. So as I was saying, the idea was to morph the data. Here at the lower level, you can see that from the 10-year, we got at the end a 10-year data set for each one of the urban stations that we had, and about 8.5 years came from this modeling approach. So at the end, we had an artificial time series of temperature and relative humidity that we could combine with complementary data coming from an official weather station located outside, and then extract from that time series the typical meteorological year following one of the procedures that we have available, in this case, the ISO standard 15927. The result at the end was this one. We got to cluster the city of Madrid in different climatic zones, so to say, urban climatic zones that we designed with the cooling degrees and the heating degrees distribution in the urban area, somehow similar to how the climatic zones are created at the national scale here in Spain, for example. The different climatic zones that we have correspond with the cooling and heating degree days that is like highly corresponding with the heating and cooling degree days. And in a similar way as well, we created a set of weather files organized in these two, or with these two axes, increasing in winter severity with the letters and increasing in summer severity with the numbers that you see here, in a very similar way as the technical code here in Spain, for example, does. The results that we obtained from this.
Thanks, Miguel. Unfortunately, time is finished.
Oh, we are. Okay.
But you can continue later, perhaps in the next session. It's a big exercise to have a lot of things to say in 10 minutes, but we will have specific questions for you later. Thanks so much. We now shift and leave the floor to Agnese Salvati from Politecnica in Catalonia. Please.
Hello. Can you hear me well?
Very clearly, please.
Okay, hello everybody. Thank you for inviting to this very interesting webinar, really. So my short speech will be on the impact of reflective materials on outdoor and indoor microclimates, that I think is quite related to the topic of the European project and this session. So, sorry. Briefly, who am I? I'm currently a lecturer at the Department of Architectural Technology at Polytechnic University of Catalonia, the School of Architecture, that's it. But I worked before the UK at Brunel University, London, and I carried out a joint PhD program between Sapienza University in Rome and UPC. And my topic, my research topic is the PhD thesis dealt with the interrelationships between urban morphology, heat island intensity, and building energy use, basically in the Mediterranean context. So I analyzed Rome and Barcelona. But I thought that for this webinar, it was interesting to present some results of another project I carried out in the UK at Brunel University, and the project was urban albedo computation in high latitude locations, an experimental approach. And the aim was to assess the impact of urban morphology and materials properties, more specifically solar reflectance, overall urban albedo of urban textures, and how these affect outdoor thermal comfort and also building overheating risks, so outdoor and indoors impacts. Okay, and so the urban albedo is defined as the ratio of the outgoing to the incoming shortwave radiation at the upper edge of the urban canopy level. So we analyze what happened in the urban canyon. So how the reflectances of facades and roads basically contribute to reflect solar radiation out of the canyons. And these, of course, involve both the property of the surfaces, roads and facade, but also the form, so the canyon geometry. And this is important because we know that lower values of urban albedo have impact on the heat island effect, outdoor thermal comfort, and indoor thermal comfort or overheating risk. My specific task in this project was the modeling task, and so an assessment of different scenarios with varying values of solar reflectances of facades and roads, and the impact on indoor operative temperatures and outdoor mean radiant temperature, air temperature, so the variables that affect outdoor thermal comfort. The project also involved Kent University and Loughborough University, so we also had a measurement on a physical model that you can see in the central picture, and in situ measurement in a residential area of London, along with this microclimate simulation and building performance simulation. So very quickly in the in situ measurement, we tried to understand what was the actual variation of urban albedo of urban canyons in a residential area of London. So taking measurements at different height in urban canyon. And the scale model was a big model, a 1 to 10 scale model, in which we measured the impact of actual materials, so bricks, different kind of paintings, curtain walls, or concrete pavings and grass, and how these materials affected the reflected radiation out of the canyon, also at the roof level, always. So quickly, some results investigated using EnviMat of changing the reflectance of facades and roads. What we have found is that, well, this is a representation of calibration of the EnviMat model. So we compared the measurement with EnviMat predictions, and we found that the performance is good, except that probably there was an overestimation of the reflected radiation at the street level compared to the measurement we took in London. But the overall performance was good. So what was it? Was then to activity to compare different scenarios, changing the facade at the part, at the upper part, and the road reflectivity at the scenario that mostly impact on urban albedo is changing road reflectivity. So an increase of the solar reflectance of the road, which is the scenario R05, as contributes to increase urban albedo much more than changing the reflectivity of facades, for instance. On the other hand, this positive contribution to urban albedo of the road reflectivity depends on urban geometry. So the impact is much more evident in, let's say, urban canyon, like the geometry on the left side. So a ratio, an aspect ratio about 1 or less, while the contribution of the road reflectance to the urban albedo is much reduced in a narrower urban canyon due to urban geometry. And even if solar reflectance of road has a positive contribution on urban albedo and so on higher temperature, there are also negative impacts on outdoor microclimate, like an increase of the mean radiant temperature at the street level. And therefore, if we want to assess the impact on outdoor thermal comfort, probably we would say that it's not advisable to increase the reflectance of the road. And finally, when we change the solar reflectance of the roads, we also have an impact. So changing the solar reflectance of the road affects the urban albedo, the mean radiant temperature of the street, but also the indoor operative temperature with a slight negative impact, let's say. So finally, we wanted to highlight that the space of the urban canyon, the outdoor environment, the indoor environment in street canyons are very much correlated, and we should analyze all these impacts together in order to define what is the best strategy in order to improve the resilience toward climate change for the future. It is a problem in London, and of course it will be even more evident in Southern Europe. So these are the main publication related to this project, where there are all the details about method and results. And I think I finished, and so I wanted to be very, so this is a very short description of the model, but just trying to highlight the most important results. I'm open to question and provide more details.
Thank you, Agnese. It's really nice.
Thank you.
Thank you.
Agnese, the next speaker is Massimo Palme, which we invite to share his work. It's very aligned to Agnese, the topic, as the presentation will be about reflecting material on outdoor and indoor climate. Please.
Well, good morning to everyone. Thank you for this invitation. I titled the presentation Local Urbanized Land Mitigation through Green Roofs in Mediterranean Environments. I'm associate professor at the Universidad Técnica Federico Santa Maria in Valparaíso, Chile. And my presentation basically, the next, I only see the first slide.
By
yes.
clicking on the screen,
I will try to answer to two very important questions by using two examples of the use of different tools to estimate the efficiency of mitigation strategies related to green roofs in two cities of Mediterranean climates. The first big question is which strategy for which context, because the intensity of urbanized land phenomenon depends on many factors, among urban fabrics, geomorphological conditions, and of course the macroclimatic emplacement. And depending on these boundary conditions, the efficiency of one or other mitigation strategy can be changed in an important way. In some environments, maybe blue solutions at urban scale can be better, or in coastal environment, the use of breeze can mitigate with good efficiency the intensity of the urbanized land. And in another context, green solutions, green infrastructure, or green roofs can be better. The second question that I will try to answer in this presentation is which strategy should be used, which tool should be used at which scale of intervention. Because of course that the urbanized land is a city phenomenon, normally more intense in the city center than in surroundings, but many studies recently put in evidence that there is a presence of local hotspots and cool spots that can be used to mitigate, or can be assessed in a more precise manner to put in the hottest spots the strategies more effective to contain and counteract the phenomenon. So probably a different scales of intervention, different methodologies for investigation should be used. Next. In this presentation, I will focus on green roofs as part of the envelope strategies to contain the impact of the urbanized land in the Mediterranean environment of the city of Barcelona and Valparaíso, and at two very different scales. In the first example, we will focus to the whole city and to some sector with most important effect, and in the other case, in Valparaíso, a very local study, and by using a different tool. In the first case, Invest, that is a tool that works on QGIS, and in the second case, met as a part of a graduation thesis of a student in construction engineering. The student analyzed the case of some neighbors of Valparaiso. Next. As a macroclimatic context, both examples are placed in Mediterranean climates. Mediterranean climates are normally can be found in all across the world. The original name comes from the Mediterranean Sea basin, but we have very similar climates in the Pacific coast of both North and South America, and in a small coastal parts of South Africa and Australia. And the urban fabrics that we find in this Mediterranean context can vary quite a lot, from sprawled cities like Los Angeles in California to big blocks organized like in the case of Barcelona, Athens, or some parts of Rome, and very dense environments in the case of the North American, North African cities like the Kasbah of Beirut, Algiers, etc. Next. In the study of Barcelona, this is a very small exercise, really. It's not a whole research project. We use the data coming from the Urban Atlas definition for the land use typologies, coming from a European project of some years ago. And we decided to focus with the intervention to place green roofs only on the sector with more people exposed to the urbanized island. So we select to act only for the blocks where a density is more than 0.05 person per square meter, or about 20 square meters per person in these zones. In the case of Barcelona, this is the Barceloneta, Sants, and some parts of the Raval and the Gothic neighbors, and the Horta and Guinardó in the eastern part of the city. Next. We use the strategy to put the 50% of the roof surface, put green roofs on the 50% of the roof surface in the selected blocks, and we changed the properties of albedo evapotranspiration and also the runoff retention of the surface where we place the green roof. Next. A visual understanding of the results. This index is a cooling potential of the urbanized island with respect to the maximum intensity of the whole city, and we can see that where the green roof are placed, there is an important effect of reduction in the urbanized island intensity, or an increase in the cooling potential that is calculated by INVEST. Next. The general result is about a 30% of reduction in the as a local effect, but there is almost no global effect. So this is the average intensity for the whole city is not changed. But this mitigation strategy relates to the exposition of the people, so it's very effective where it's more needed, and it is a multi-risk mitigation strategy, because also the runoff is reduced in about 40% in the target blocks. Next. There is, of course, some limitations. INVEST is very simply in the calculation. There is only the surface effect, no ventilation, no coastal breeze included, no three-dimensional assessment. Next. So coming to the other example of Valparaiso, Chile. In this case, we selected the places where the urbanized land is more intense. Next. And we modeled some blocks with the EnviMet tool. Next. The strategy in this case was to check an intervention of all the roof surfaces with a 0, 50, or 100% of roof intervention. We changed also the albedo and evapotranspiration properties in the model of the same tool, EnviMet. And we conduct a set of simulation at different days, different hours. I will show just one. Next. This is at about 8 p.m. in the summer solstice, and we can see the difference from 0 to 50 and 100% of coverage on the roof. Next, I finished.
Okay, we have to thanks so much, Massimo, for staying time. We continue perhaps the conclusion later in the question and answer session. Thank you very much. Remarkable cases. And we shift to our friend Francesco from Tallinn, Taltech, and the floor is yours, please.
Hello, everyone. Thank you very much, Emanuele and Emanuela, for the invitation. Can you hear me correctly?
Perfectly.
I don't see I have the control of the slides anyway.
If you click on the screen, you should be able to.
Okay. Can you come back? Okay. So yeah, hello everyone, and I'm Francesco De Luca. I work as a senior researcher at Tallinn University of Technology. And the work I'm presenting today, urban shadered building form generation method for reducing energy use in the built environment, is the most recent step of a research trajectory to develop building massing methods in consideration of environmental and climatic performance of the built environment. A previous step of the research has been that to develop a method that we call the reverse solar envelope method, which generated building massings or something in the middle between building massings and solar envelopes in consideration of solar access of existing premises. The interesting aspect of this method was that the user, the designer, could select in different ways the sunlight hours. So in this way, it was possible to generate different variations of the building massing through the elimination of three-dimensional cells of an hypothetical maximum volume subdivided with these three-dimensional cells. And at the same time, with this method, it was possible to perform some initial performance analysis on the future building massing. And this method, the reverse solar envelope, has been included in a tool that we developed for Grasshopper to develop solar envelopes through different methods. Now, the most recent method that I'm presenting today, that we call urban shadered, is an advancement of this method that we have very briefly seen. And at the same time, it is grounded on existing methods for the design of shading devices, which are the cellular method by Kaftan and Marsh, and the shadered method by Sergeant, Niemals, and Reinhardt. How these methods works? They subdivide an hypothetical shape of shading device in cells, and then they perform heating and cooling load simulations to evaluate the so-called desirability or undesirability of each cells in relation to the obstruction of the cells when heating and cooling is occurring. In this way, then generating an optimal form for the shading device. So we applied the same principle to an urban environment to investigate if it is possible to generate a building form which could decrease the energy use of surrounding premises, thus having a positive effect on the existing built environment. Again, here we are using a maximum buildable volume subdivided in three-dimensional cells. And the assumption is that a cell blocking beam solar radiation during a certain hour would reduce cooling energy if present, or would increase heating energy if present. and almost surely would increase electric lighting use if present. On the contrary, the absence of a cell would have the opposite effect. So comparing to the methods for generating shading devices, we expanded the method, including also electric lighting, and we also considered the level of desirability or undesirability of a cell, taking into account a shading factor, which is the size of the obstruction of a cell on a window, and the beam factor, which is the quantity of the beam energy during every simulation time step. So we can say that the effect of a cell in blocking beam solar radiation can be positive if cooling energy is larger than the sum of heating and electric lighting, and can be higher if the shading factor and the beam factor are large, or the effect of a cell can be negative if the sum of the heating and electric lighting is larger than cooling energy, and can be worse if, again, the shading factor and the beam factor are large, or the effect can be neutral if there is, in that for that specific time step of the simulation, there is no energy use, no window obstruction by the cell, or no beam energy taken into account. So the algorithm then summed all the effect for each time step for each cell against each window. So it determined the effect of a cell on every window, and consequently the algorithm summed the effect of each cell on the entirety of the window taken into account, in this case 3 for each surrounding buildings, so that we could determine the cells with the positive effect, those with the blue color, which are the cells that allow to reduce the total energy use of the surrounding premises, or the cell with a negative impact, that are the purple one, which actually increase the energy use of the surrounding premises considered as a whole, and the cells with a neutral impact. Okay, then to test the method, we generated a parametric workflow considering we wanted to generate a large number of urban scenario variations. So we considered that we tested the method in 3 cities at 3 different latitudes with different climates, Tallinn, Paris, and Athens. And in 3 different urban environments, we considered building use as office and residential, which make a very different use of the different type of energy, cooling, heating, and electric lighting. And we also considered the 3 window to wall ratio for the test room. At the end, we get when we consider, let's say, the cells with the positive or neutral effect, then we tested these cells against the sunlight exposure requirement of the current European daylight standard. So we can see in this diagram that the white cells are those that have a positive and neutral effect, and at the same time also guarantee the required sunlight exposure as required by the minimum, let's say, requirement of the European daylight standard. So at the end, we generated what we call an energy solar envelope, or a conceptual building mass, which is supposed to have then a positive effect on reducing, let's say, the full energy use of the surrounding premises that we took into account. And the results are encouraging, let's say, promising, because actually all the in all the urban scenario variation, the conceptual building mass allowed to, in few cases, to let's say to have for the surrounding premises the same energy use, but in most of the cases, this conceptual building mass reduce the energy use of the surrounding premises considered as a whole, and obviously in different way in the different climate for the different cities. So it is much, let's say, more performative in southern and hot climates, for example, in Athens than in Tallinn, but it still performly very well, let's say. Okay, then moving on, the main question would be, okay, but how do we use this energy solar envelope to design, let's say, conventional buildings? Actually, this is a sort of next step of the research. Even though there are examples of, let's say, high-end buildings using this type of pixelated building form, still, let's say, if we want to make this method as a tool available for designer, we have to, let's say, improve the usability, among other things. So actually, future work is exactly improve the usability and constructability of the conceptual building mass, and how. Actually, the first idea, but we still have to start to work on this actually, is that to use larger sets. The sets that we have seen have the size of 1 floor-to-floor height, about 3.5 meters. So we believe that if we consider larger cells, like the same size as 3 or more floors, it would be easier to realize more constructible building mass. And also it would be interesting to give the possibility.
Thank you, Francesco.
Okay.
Yes, actually, the slide, the previous slide was perfect to leave some space for future. Thanks so much. Wonderful presentation. We meet in the panel in a bit. We leave the floor now to Angelos, and I ask also the help of the staff at Build Up to handle the control and the sharing to Angelos. Hi, Angelos.
Hi.
Hello, can you hear me?
Yes.
Excellent. And I'm not sure which screen I am sharing.
We see your screen now. Yes. You have 10 minutes starting now. Thanks.
But do you see my presentation screen, or because I'm not sure which screen you're seeing?
We see it. Yes.
Okay, super. Okay, so, well, hello everyone. 10 minutes. I will try my best to be on time this time. So yeah, I will be talking about infrared, the intelligent framework for resilient design. Sorry, I just want to move this window over here so I can see your faces as well. So yeah, I am Angelos Kronis. I am the head of the City Intelligence Lab at the Austrian Institute of Technology. And I'm also co-founder of the infrared platform, software platform that's now spinning off as a new company. I'm going to talk about it very, very briefly. So first of all, a couple of words about the AIT. Austrian Institute of Technology is the largest non-university research and training organization in Austria, has different centers, different units. We are in the digital resilience cities unit, and our expertise is focusing on 3 research fields: climate adaptation, climate resilience, energy and energy transition, and smart cities, as well as integrated urban systems and planning. So within our unit, we have different expertise. We're working across different scales, from the regional to the block, and from the let's say across different disciplines, from mobility to microclimate, accessibility. So like just a couple of words of where we are, just to give you an idea. And all of this comes together in the City Intelligence Lab, which is what I'm heading, which is a laboratory that sort of like aims to integrate all the different expertise, the different analysis, the different simulations, because holistic decisions need different approaches. So what we're trying to do in the CIL is bring together all of the sort of like different analysis, climate analysis, as well as other analysis for the city, to be able to develop more sustainable plans. So I'm going to very briefly talk about what we're doing so that I can show what infrared is and why we came up with it. So we're working a lot with urban planning. Of course, we're working with sort of like automated generative planning, and we've partly developed decoding spaces alongside with Bauhaus University, ETH, and the Future Cities Laboratory. And essentially, decoding spaces allows you to very quickly sketch urban form, to sketch sort of like street layouts, or to sketch parametric typologies, which we can very quickly apply to test different scenarios, which is very relevant to what we're doing on the climate side, as well as sort of like, very quickly sketch completely new, let's say, developments in areas that have essentially no planning yet. So it's a very interactive and generative sketching tool for parametric modeling. So we can also do like whole master plans with crunching a few numbers, etc. But we're also working a lot with, as I said, analytics, where we're looking at accessibility, mobility, how you can access different things in the city. So in this case, looking at isochrones, what you can access within a certain amount of time, and how that sort of like affects transport models and transport networks, and how you can optimize transport networks by sort of like moving things around. But coming to the climate issue, we have been working a lot on climate simulations here. This is, for example, rainfall off simulation that we've been doing, we've developed in-house, which is for the city of Vienna. So you can see how rain falls through the city, identify flooding areas or potential buildings that have resilience needs, like buildings with basements, etc. And the problem with simulation, this is where I'm getting to, is that it takes a lot of time. So like one of those simulations might take up to 8 hours to run. So that's why we've developed infrared. This is what I'm going to talk about today. So infrared is essentially an AI-driven simulation prediction framework. So it allows you to essentially predict simulation results without really running them. So like instead of like taking 8 hours, or if we look at the example of wind comfort, which is a little bit more complex even than rain, you can take up to 3 days to start, prepare, export mesh, or whatever you have to do, the steps to really get to the result. And then infrared predicts that same result with about 90 to 95% accuracy within a second. And that's like a really big breakthrough, because it changes completely how you can essentially integrate simulation in design. You can actually get performance right at your hands when you are making decisions. So this is probably the best, and of course this is done through AI, right? So through deep learning models. So this is probably the best example. You have a solar radiation simulation on one side, and then you have a simulation prediction. One takes half an hour, the other takes milliseconds, and it shows essentially the potential. To do that, of course, we have to take cities like Vienna or other cities around the world. We parcel them, we create 3D models, and then we run thousands and thousands of simulations with which we are training essentially our machine learning model. So this is essentially the comparison between the input and then the simulation and the prediction to show you a little bit how different geometries have a different effect. And the accuracy, as I said, can go up down to 85%, but it can go up to 95, and actually 85 is in the worst case scenarios. And we've also used a lot of like both synthetic and actual real data to model the parametric like models that are needed to simulate the results. So currently infrared works in 3 different models, like heat, like essentially solar radiation, sunlight hours, and wind, and CFD, which is essentially wind comfort in our case, but we are already trying to do noise, rain, and traffic. And it actually works also in a very sort of like integrated way. So it has both a cloud app where you can go online and design and get immediate answers. You can have a Grasshopper plugin, or you can also have an API which allows you to directly connect infrared simulations to any sort of like other software module that you care about. So that's what like infrared looks like when we're using it on the different sort of like ways, like whether it's the web app plugin or essentially using an API. And I'm going to go through it a little bit like in more detail. I think I am more or less good in time. I'm 5 minutes now. So this is how the cloud app looks, and then I'm gonna try to show how it's working when you're creating a project. You can type your location. Essentially, it gives you essentially an OpenStreetMaps context which you can use in case you don't have any context. In this case, it's the Vienna International Center. And once you have that context, you can sort of like create a project and integrate that context, and it essentially downloads those very, very simplified 3D models. But these are good enough for a sort of like first step. I'm going to bring in the project very quickly, and then once you do that, you can start sort of like manipulating that context of like setting your site or whatever. But then here's the important part: you can add the different analysis you care about: wind comfort, wind speed, solar radiation, and sunlight hours in this case. And then you can start already designing. So I'm going to create a really badly designed building. I'm not really an architect. I've a failed one. So here's a very bad tower design. But then once I click, let's say I click analyze, you can see how quickly the results come back. And there will be results for wind, solar, and sunlight hours, as I said. So just very quickly going to it. I'm not skipping that part just to show you essentially this is actual time it takes on the web to get the results back. And yeah, the idea of like, you know, having wind comfort at your hands in this sort of like very direct way changes a little bit how you design with the wind. I think the next example where we have, you know, essentially infrared in Grasshopper is actually more interesting in that sense, because we can see how we can essentially take a park and move it around and immediately be able to see in a chart how much of these areas that we have in the park are like comfortable, uncomfortable. How does the wind regime, you know, operate in this? This is Norway, for example. This is a project we did with Link Architecture. How does it like look when you're changing things, and you immediately get this feedback on the chart. And yeah, going one step further, if you actually want to sort of like develop something even more complex with infrared, you can do that through the API. So this is Giraffe, which is a web-based urban planning tool that's developed by colleagues, UNSW and some other, and this is essentially a company right now. So you can essentially see how infrared is integrated in a completely different design system, because they've just used the API to integrate directly the simulation results. And you could of course do that in any other system. Going very quickly to make sure that I am on time, essentially this is what it looks when you're trying to, and I'm gonna pause this video for a second, like when you have this ability to just do like simulations so fast, you can run parametric models and generative models that allow you to both you know, run thousands of different iterations, but also to test them and evaluate them and get the performance results. So here we see one small like block, and how essentially we run 1,000 different options on that block, and we have all of the simulations together attached to each one of these options, and then you can essentially select the ones that are performing the best and bring them back to the table and continue working with them. So that's like really changing a little bit how we design. So we have like here AI models, apart from the AI simulation models, but we also have AI models that help you like fine tune your design. And in this case, for example, we have a design of a tower, and we want to find out where exactly that tower should be in that sort of like quarter, and then essentially yes. And that is actually done.
In time.
Thank you so much. Yeah.
Yes.
I'm going to stop sharing.
So it has been a very a pity to interrupt all the panelists, but we really got a glimpse of each of you. So if you can turn on your camera, please. So super session as the previous one. The debate revolved a lot around matters of form and material. Perhaps, yeah. We have also Carmen. Yes. Carmen perhaps joining if she's online. Wait, you're in the next session, but very good that you're already with us. It's great to see you anyway. So actually, we have only 10 minutes. So we want basically just in one sentence to ask you what is or what will be the impact of your research. We will begin with Carmen, but as a vast array of project, and I wanted to ask Carmen just in one sentence, how does she see her array of research being implemented in the city of Sevilla, where these studies are taken? Of course, we have just 30 seconds for each of you, but we had a question from the audience that move in this direction, asking how are these things implemented? Thanks, Carmen, for taking this question.
Thank you, Emanuele. I think we just like to say that we are focusing in the inhabitants, because it's really perceived that we have serious problems here. Just after the lockdown, after the coronavirus, the sensation here was we have another lockdown again, because it was the end of June and there was no way to go out in the city because of the hot. So
sure, fantastic answer.
We're really suffering at this point, so we're focusing that. Sorry for that.
Sure, and we will try to share all the slides, because the group led by Carmen has an incredible array of research, and it was a pity to interrupt. Okay, thank you so much, Carmen. And Miguel, the question was, are you also accounting in for future climatic projection? And if not, how will you?
Sorry, accounting for what?
No, it's a question for Miguel. Yeah.
For future weather projections, right?
Yeah. Yes.
Yeah. No, not in this case. It is not taken into account, but we are definitely thinking about it and trying to incorporate it in the future, maybe supporting in other tools as Metronorm or other areas in which to morph the data, not just to urban ambient or to urban areas, but also into future weather.
Thank you so much, Miguel. Agnese, you had an interesting statement about high albedo being a problem for outdoor comfort, in the sense that much of the shortwave may be reflected towards the human body. But today we have several plans that do not account for this factor. How would you approach the topic? Is it better to have, in certain contexts, intermediate albedo materials?
Emanuele. Sorry, I had a connection problem. I couldn't hear the question. Can you repeat it?
Okay. Yes. Just if you have any consideration about using medium albedo material in certain contexts, because as you show, the short wave may be targeted to the human body, therefore creating contributing to certain discomfort. Okay, I think we lost
yeah, there are. I mean, yeah.
Please, Agnese,
can you hear me?
Yes.
Yeah. Okay. So there are. I mean, the analyzing of different scenarios show that we can use solar. We can increase solar reflectances to have a good impact on the heat and effect without worsening outdoor thermal comfort. So probably the best way will be we can increase the albedo of roads, but leaving like the pathways where pedestrian walk like a bit darker, and also the bottom part of the facades. These are basically the results. So we should try to avoid that the multiple reflection go directly to the human body. So we can use.
Thank you so much.
The next question is for Massimo Palme. And Massimo, we want to ask you if you identified some difference in these two case studies that you present that are classified like Mediterranean areas, but in two different countries, really with really different climate conditions. So what's
yes,
in two words?
Or if you know, yes. Well, the example I showed, they have a very different tools that we used, but I know the condition of Barcelona and Valparaiso, of course, and I can see that, for example, in Valparaiso there is a microclimatic condition quite different because of the influence of the Pacific Ocean. So we have very much more wind, and these effects are for example, very important for cool the city. I think that our research should go to find a way to better communicate the importance of the result. I think that some big scale analysis like the INVEST tool permits can be used to facilitate the stakeholders to take decision, and then in local sector we can analyze with EnviMet or other tools much better.
Yeah.
And to yes. Put all together, like Angelo showed, is I think the best thing that we can do.
Good link to the next questions.
The next question for Francesco, and we want to know if you put in practice your methodology already, or did you think to put it in practice?
Are we talking about the infrared? I think infrared infrared is a source.
It was a question for Francesco. Sorry, Angelo.
Sorry. Sorry. I thought that was me.
Francesco, you're on mute.
Okay, yeah, the answer is, let's say not yet, in the sense that these methods are sort of initial methods, and what I'm planning is that to at least having the possibility to develop let's say develop a larger research project in which different professionals could be invited to participate, to give a suggestion, and for example on the usability of possible tools developed with the method. So far it is just the development of these methods, not yet the application. So the application should be involving professional, other researcher in parallel fields, and hopefully with a larger research funding, for example.
Okay, fantastic. We take the last question, which was from the public, which is for Angelos, if the tool is available for several locations or it will be.
Yeah, thanks for the question. The tool is, the wind comfort is available for anywhere in the world. It's agnostic to location. Solar radiation light hours is still in development, that we will develop by 100 cities. And yes, the tool is available to use. You can email me if you want to, or like reach out if you want to get a license or like try to use it.
Fantastic. So the rhythm has been very, very, very fast. And it's probably a format that we hope the public will appreciate, as we definitely don't lack to have a certain diversity of sharing your knowledge. We want to thank you very much. It has been impressive to listen to Carmen, Agnese, Massimo, Miguel, Francesco, and Angelos. And also each of you share their contact, so all the more than 100 attendants feel free to contact all the speakers separately. We have to thank you very much.
Thank you very much.
Briefly to the next session, which is session 3. The topic is on climate change, and we will offer also a modeling overview. The speaker will be Giandomenico Burro and Salvatore Carlucci. Staying in Cyprus, we will have Nestoras Antonio from the University of Cyprus. Then we go to Lund University, where we have Professor Vahid Nik and Kavan Javan Rodi. And then we close the session with Alberto Martini, that works at CMAT, but is remotely connected from US. Therefore, to stay on time, we leave the word to Giandomenico, and you have 10 minutes. Cheers.
Thank you. Good afternoon, everybody. Oh, sorry. I'm Giandomenico Burro, a PhD candidate at the Cyprus Institute, and today I'm going to speak a bit about the research project that I'm developing here at the Cyprus Institute. The title of the project is Cooling the City, Mitigation of its Extremes through Adaptation Strategies for Cities in a Semi-Arid Climate. And actually, the motivation behind this study is led by the fact that, as we know, the link between human activities and the warming of land, atmosphere, and ocean has been proved unequivocally. For instance, global average air temperature has increased by 1 degree compared to the pre-industrial level, as well as the global surface temperature has increased by 1.59 degree compared to the reference period that is from 1850 to 9000. So all these changes are mainly caused by the continuous rising of greenhouse gas emissions, and also due to land use changes. But if from a global perspective, the climate change is as a straightforward path, this is not happening from a regional point of view. Because of different geographic characteristics, some regions seem to, let's say, warm faster than the global average. And this area are defined as climate change hotspot. And in particular, the Eastern Mediterranean and Middle East region is defined as a prominent climate change hotspot because of its particular geographic location at crossroads of different climates, and because of its diverse meteorological characteristics. The region is very sensitive to change in large-scale climatic dynamics. Besides these meteorological and geographical issues, the region is facing other sensitivities like geopolitical or religious problems, as well as the region is facing a robust urbanization and a very fast population growth. So here the built environment is a very clear example of land use change. That is one of the problems that is exacerbating the climate change. So built environment, urban environment is a human-made environment for activities, and it can range across different scales from buildings to neighbors up to cities. And cities in particular are defined as receptors and drivers of climate change. We all know that cities are usually warmer than their surrounding area because of the presence of some factors that trap and release heat, and at the same time, they lack of natural cooling influences. So we can describe the built environment according to these different urban units, as you can see here, and they again can range across different scales from 10 by 10 meters up to urban region like 100 to 100 kilometers. And all these units can be defined can be affected by different urban climate phenomena. So, as you have seen, we have different level of detail of city representation that ranges across different horizontal scales, as this slide presents here. And of course, we have different modeling and simulation approaches that can be used according to the user needs or to the scope of the research. So, since my research project will try to merge this domain from the city up to the building, now I will show you some of the gaps that I found during these 2 years of PhD. So I find out that models at different scale provide a not detailed description of the built environment, and in particular for the Eastern Mediterranean and Middle East region, there is a lack of studies that adopt advanced urban canopy models. At the same time, it's still difficult to identify a tool that considers all the city's fluxes, and the parameterization required by the urban canopy models in order to describe the city is very general. Okay, these are the research question that I want to answer in order to fill these gaps. But now I wanted to show you some preliminary results that are focusing on the atmospheric part of my work, because I will try to merge 2 different models, one from the mesoscale side, that is the WRF model, and the other one from the microscale side, that is ENVIMAT. So with regards to the atmospheric side, to the mesoscale side, I set up a domain that focuses over the Eastern Mediterranean and Middle East region at 12-kilometer horizontal resolution. Inside this domain, I created a nested domain with a 4-kilometer horizontal resolution over the Levant region, as you can see here. And finally, an innermost domain over the area of Nicosia at 1-kilometer horizontal resolution. So I ran some test simulation for the period that goes from the 27th of July 2021 until the 5th of August 2021, in order to compare the performance of 3 different urban parameterization schemes: the bulk, that is the simplest one, the BEP, and the BEP plus BEP. And the variables that I investigated were the mean air temperature and the extremes temperature. But before showing you the results of this performance simulation, I want to show you something really interesting. As you can see here on the left, we have a picture of the area of Nicosia taken from Google Earth. And on the right side, you can see instead the representation of the built environment for Nicosia according to the land classification modified EGPB NOAA. That is a land one of the default land classification available inside the WRF. And actually, you can see how different is the representation against the reality. So, at the same time, BEP and BEP plus BEM requires more built environment data that can be retrieved from the WUDAP, that is the World Urban Database and Access Portal tool. This is an online platform that allows people to retrieve and access coherent data on urban morphology and information about built environment useful for the simulation. And among these tools that are available on this website, there is the LCZ generator that is actually, again, a web-based platform that allows people to map and classify according to the LCZ classification SCT of interest. And the final result of this classification is exactly the one that I'm showing here you on the left-hand side. So once we got this data from the WUDAPT, we use them to a Python script actually that is called WUDAPT to WRF in order to make this information readable by the WRF. And on the right-hand side, I'm showing you the implementation in the land classification, on the baseline classification, implementation on the LCZ classification. And actually you can see how much the built environment representation is improved compared to the previous one. So now moving on the results, here I'm presenting just some very brief and quick differences between the different schemes against the temperature differences. So we have BEP minus bulk for the simulation period and BEP plus BEM minus bulk. And as you can see, the BEP has a cooler temperature over the city, while the BEM has higher temperature. And actually this cooler behavior of the BEP is something of counterintuitive that will be investigated in much more detail, even though in literature I found some other works that found the same results. Last thing that I want to show you is the comparison of observed and simulated temperature extremes during daytime. The observed data were provided by the Cyprus Department of Meteorology, and they are presented according to this red line here, while the results of the simulated temperature are taken from a grid box nearest the observing city center station. So as you can see, more or less all the schemes follow the same trend of the observed temperature, but overall they underestimate the temperature. So in conclusion, what I want to say is that right now the schemes, as you can see, follow the variation of the observed temperature. So this means that the model is working properly, but we need to understand why this BEP scheme is behaving in a cooler way than the bulk that is the simplest one. But the thing that I want to highlight is that the LCZ.
We finished the time, but I think the conclusions are quite clear, and the presentation will be available. Thanks so much, super interesting. Thanks also for Salvatore for being with us.
Thank you so much.
So we are going to involve you in the panel session discussion after all the speakers. So we stay in Cyprus, and we have Nestor Antonio that recently, well, actually a few months ago, finished his thesis, and we ask Antonio to stay in the 10 minutes if possible. I know you have a lot to say, please.
I will do my best, yes. So hello everybody. Thank you Emanuele and Emanuela for your invitation, for the chance to present my results. So I will briefly explain you, just a minute. Okay. So I will describe the process of creating a numerical model for predicting the impact of climate change on urban microclimate. So in the context of climate change, we're expecting that some serious impacts will happen on the urban population, and this has to do with increased air temperatures, heat waves, frequency and intensity of heat waves. The urban heat island effect will be intensified. So in order to investigate the impact of climate change, we need first to understand deeply the complex urban environment. So we have selected a case study area, which is in Nicosia. And it's very complex urban area, typical Mediterranean style, I could say. There is a high-rise building in the middle. And the three, we have investigated what are the typical methods that are used for investigating the urban microclimate. So we have field measurements, reduced scale wind tunnel measurements, and computational fluid dynamics are the most usable methods. And each one of these methods has its advantages and disadvantages, and we decide to combine these three methods to have the best possible result. So the first part was to conduct field measurements in the case study area. The measurements were of very high resolution and multi-scale. The scales were that the measurements were performed were the regional scale with radio soundings, city scale with 5 different meteorological stations, neighborhood scale with aerial thermography mobile stations, and street scale with thermocouples and ground-based thermography. And through these results, we're able to examine the complexity of the urban microclimate in terms of surface temperatures, the materials, and we were also able to track specific phenomena that seem to act to intensify or reduce the intensity of the urban heat island effect, like sea breeze and winds coming from the mountains. So the next part was to develop a CFD model and validate the CFD model for predicting urban ventilation. You can find more information on the reference publication. So this is the CFD model, wind tunnel model. We have used the wind tunnel in University of Gävle, Sweden, and the model was in a scale of 1 to 250. Measurements were taken in 38 different vertical lines in more than 1,200 points for turbulence intensity and wind velocity. And then we developed a CFD model based on the wind tunnel model to assess the performance of the CFD model of predicting urban ventilation based with comparing with the wind tunnel results. So results were quite satisfactory, especially we have, especially for LES, we have compared two different turbulence modeling approaches, LES and RAMS. LES is much more expensive in terms of time, but seems to be quite accurate. So we have also evaluated the different locations of the city in terms of ventilation effectiveness, and building height variability was found to be an important morphological parameter that enhances urban ventilation. So the next part was to use this model to evaluate the urban microclimate in terms of air temperatures, surface temperatures, You can find more details on the reference publication here. And these are the comparisons with the predictions and the measurements. The measurements that we have used is the ones that I described in the first part. So we have used measurements to evaluate the model. This on the top is a thermal image taken from a helicopter. The bottom is the CFD results. You can see that there is quite a good agreement, but we have identified which are the worst agreement in which locations, and the main reasons were the simplifications of the CFD model, vegetation, materials, and so on. And the last part was to use this model to predict what will be the climate change impact on urban microclimate. So the methodology was to use the field measurements in combination with numerical climate prediction models. We have used the data from the Eurocordex database to have the projections for climate change. And we have used this information as boundary conditions for the CFD simulations of the validated model. And together with radiation modeling, we have used all this information to investigate what will be the impact of climate change on thermal comfort using the UTCI as an indicator. And the results show that there will be a maximum 2.3 average increase of the air temperature. This is a couple of locations. We have several locations that we have compared. And this will, based on published method.
We need to stop. The time is over. Okay. Thank you very much. We can discuss in the discussion session. So the next one is Vahid Nick and Kavan Yavanrodi. Thank you.
Yes. Can you hear me? All right, great. Hello, everyone. I'm Vahid Nick, professor in Building Physics Division at Lund University, and my colleague Kavan Yavanrodi also will join for this presentation today. We have done research about the impact assessment of climate change on buildings and energy systems for several years. So we try to quickly give you overview today. So when we are dealing with climate change, there are two approaches. One is, two main concepts. One is climate change mitigation. The other one is climate change adaptation. So mitigation is what you usually see about, how to prevent or slow down climate change. And many are doing this LCA research here. But when you are talking about this climate change adaptation, it's answering questions of how to face climate change, how to decrease future risks. And then climate resilience comes as one part under this climate change adaptation. And when we are dealing with climate resilience is when we are answering questions about what should we do to pass these extreme climate events safely. So this resilience comes with these extreme conditions. And then for doing, let's say, this climate change adaptation, or even have a good analysis of climate change mitigation, we should have impact assessment of climate change. And then most of the approaches that we are developing or have suggested so far are some approaches for doing impact assessment of climate change. So as you know, there are numerical models, very advanced simulations that are doing projections of future climate. One major source of uncertainty here is that there are multiple institutes, multiple climate models, and multiple also models at different scales, at global scale, at regional scale, and then we also take care of this urban scale. So, and we have several scenarios for future conditions, how we as humans will develop, how much do we care about decreasing emissions, etc. So it results in lots of scenarios for future conditions. And when we have many scenarios, we have many data sets and we have uncertainties. So how should we do the assessment? That's the question. So the challenge is here, there are many plausible scenarios. All of them are plausible because all the models that are out are verified models. And there exist several scenarios and many data sets. And then when we are looking at the urban scale or cities, we have many buildings, a human being, a big source of uncertainty, different ways of living, and then we have this urban infrastructure, for example, energy system, sewage system, whatever. So there are lots of, let's say, interlinked systems in one city that are affecting the performance of buildings and cities and energy system. So our major focus has been buildings and energy systems. So in buildings, for example, we have different systems, different users, etc., different type of buildings. And then for energy system, we have different scenarios for energy transition. For example, we want to become greener. We want to decrease the share of non-renewable sources and then add more renewable sources, etc. And there can be different scenarios here. So then we will have multiple scenarios for climate change, multiple scenarios or conditions for this building, energy system, and in general urban conditions together with buildings. And then we want to do this climate change mitigation adaptation. So we need suitable climate data sets and suitable methods for do the assessment. So what we have contributed so far is that we have developed methods to generate representative future climate data sets. So the methods are working like this. We consider multiple future climate scenarios from regional climate models. So we have higher resolution, especially on temporal resolution here. And this regional climate data is the one that is suitable for our simulations. The data we get from global climate model is not suitable. We need to work on it. So, and the finest models available at the time are these regional climate models. So we get data from this. We work with multiple future climate scenarios, and then we look over into them. I mean, depending on the RCP or region or any scenario that we bundle together some climate scenarios, and then we generate only 3 sets of weather data. One is typical, one is extreme. It can be extreme warm, for example, and the other one is extreme cold. And then we have done also, we have developed approaches for this impact assessment, energy system design, and integrating urban microclimate. So these are the references you can take a look. I'm not going into that. So concerning integrating future climate scenarios with buildings and energy systems, we have published around 3 years ago one work in Nature Energy that there you can see that for the first time we are doing this direct integration of future climate scenarios to the energy system design. So we assess what are the performance of these designs, and then we take into consideration these extreme climate events. So we want to design something that is climate resilient and meanwhile is sustainable and decreases this CO2 mitigation or any other mitigation. And then recently we extended this work, and then now we are becoming more detailed and taking into account these urban climate conditions or urban microclimate, which Kavan will talk about that more. So we, after this regional climate scale, we go to this urban climate model, and we take these representative weather data sets that we have. We do this microclimate simulations, and then do let's say much finer simulation of what are the conditions for when we have extreme conditions, because extreme climate conditions are the bottlenecks of our designs or the performance of our systems, and then they can vary depending on the scale. For example, you can have much warmer conditions when you're taking into account this urban microclimate, or for example, something like heat island happens. So I think from now, from this slide is whether Colin talks about it.
Thank you very much, everybody. Right, I hope that you can hear me. Yeah, last time I had a problem. So I'm Kavan Chamarudi. I'm an assistant professor in Lund University. So as just to make it quicker, I know that we don't have time. So we're talking about a multi-scale climate model, specifically focused on the energy and, of course, energy system design and control. So that's the focus. So that's the main difference between the literature in actual urban climate studies. So we're talking about 3 levels. We call it meso for the actual the data that are coming from the RCMs, regional climate models. We have the urban climate, which could be defined as studies that using, for example, urban balance energy equations. And of course, at the finer spatial resolution, we deal with microclimate studies. So our work actually has been on this to assess first the impact of these different levels on the energy demand, let's say, and of course on the energy system design and control. So maybe you can change the slide by that. I cannot do that. Oh yeah, so there's some insight from the actual the recent publication that I showed you the workflow. So for example, we looking to 18 cities, European capital cities. We saw that how these different levels could impact the energy demand and, of course, the performance and the cost of infrastructure and grid integration of renewable energy systems in, let's say, different time scales from 2010 to 2099. And, of course, also considering urban densification scenarios in by 2050. And we saw actually it could be somewhere up to 70% only in temperature. This condition for wind is worse, so wind is harder to predict actually, as Nestoras actually in his presentation mentioned. So that is more tricky. And of course, when we're talking about temporal resolution, and we want at least hourly data for our energy simulation, that could be even more challenging, as we cannot use, for example, LES in that scale because it's computationally quite expensive. Maybe next slide, right, please. So the importance of these, considering urban morphology with not confined that to just urban form is one part of our study.
Sorry,
so
yeah,
so maybe just next slide, final one, yeah.
Thank you.
Yeah, you can just see that. Yeah, sorry.
In the panel. Okay, so next one and the last one of this section is Alberto Martilli from CIMAT. And thank you, Alberto, for your time. We know the difference hours that have between us. So thank you to be there.
Thank you for the invitation. Now, can you see me? No.
No.
Not see, but we see your presentation.
Yeah.
But I should turn, I guess, the camera on, no? Ora un po'
Yeah, the camera doesn't work, but don't worry. I think, okay, now we see you, please.
Okay, so, okay, now I can move in the slides myself, right?
Absolutely, right. You click on the screen and you have 9 minutes. Okay,
wonderful.
Thanks.
Thank you. I'm sorry, I wasn't able to attend the dry run, so I hope everything will be smooth. Thank you very much, Emanuele and Emanuele, for the invitation. I think it's a very interesting meeting for what I could see so far. So the aim of my presentation is to show you a very short overview of the work that I've been doing the last, say, 20 years on mesoscale modeling of urban operating. So, oops. If I know that I have just 8 minutes, I'll go straight to the research question that motivated my work. So mainly there are 2: how to simulate the two-way city-scale interactions between cities and citizens in the urban atmosphere, and how to quantify the city-scale impact of mitigation and adaptation measures based on the modification of the city characteristics on thermal comfort and building energy consumption, and how this measure affect air quality. So in this, here I highlighted the word city scale because I'm not focusing on just a few buildings, but I want to see the impact of these strategies of this urban overheating at the scale of the city and how this interacts with the surroundings. So what's the tool that I use? And before explaining the tool, I'd like to just briefly explain how I see the behavior of the urban atmosphere. So in particular, in the urban canopy layer, which is the most important one, because it's where people live. So the behavior of this layer is basically the result of the interaction between two scales. The micro scale, which is basically all the features that happen in this layer, which are wake behind the buildings, for example, or vortex in the street canyons, different heating due to shadowing. All these happen at a scale of a few meters. But the behavior of this layer is also influenced by the amount of exchange of heat and momentum with the atmosphere above the city, what I can call the urban boundary layer. And the behavior of the urban boundary layer is the result of features at much bigger scale. Sea breezes or land breezes or katabatic flows or valley winds. So if we want to, the big challenge of urban meteorology is try to combine these two scales, because now with the computational power that we have now, it's impossible to explicitly resolve both scales. So what I do is basically using mesoscale models. Mesoscale models are models that can be run at a spatial resolution of the order of 1 kilometer, or say, over domains of hundreds of kilometers. So you can really resolve the city and how the city interacts with the surrounding, which is a very important thing for urban climate, for example, because how the surrounding behave affects strongly the city. But so with this type of model, you can resolve these features, but you cannot resolve the microscale phenomena in the urban canopy. So you have to parameterize them. So it's about 20 years that a new parameterization of the urban canopy have been proposed for mesoscale models. And these parameterizations are basically all based on one assumption, which is an idealization of the urban morphology. So since we recognize that we cannot resolve the full complexity of a city, we say, okay, the city for us is just a series of canyons. All the canyons have the same width, all the buildings have the same width, and then you can, in some cases, account for the variability of building heights. So this is a strong simplification of the real morphology. The advantage is that since all the canyons are equal, you can estimate, for example, the shadowing in one canyon, the trapping of radiation, and resolve the building the surface energy budget for each one of the surfaces, for the road, for the walls, and for the roof. So that's the advantage of this approach. Several schemes, as I said before, have been proposed. One is the one that I started to develop in my PhD at the EPFL in Switzerland almost 20 years ago. And then we continue to improve this in CMAT. So this scheme called BEP has been implemented in WRF, which is the most used mesoscale model in the world. And in this scheme, in about 10 years ago, with Francisco Salamanca, PhD student in CMAT, we introduced a building energy model. So a very simplified model that can resolve the energy budget, basically, of the indoor environment for these very simplified buildings. And this was an important step forward, because with this simple BEM, we were able to estimate the energy consumptions in the building and also the anthropogenic heat that is emitted to the atmosphere in case you want to activate the air conditioning system. So we were able to investigate in this way the two-way feedbacks between the climate and the building energy consumptions. We continue to develop this, and now since, as I said before, one of the aims of my work is to evaluate the city scale impact of different mitigation strategies, we introduce in the model the possibility to simulate some of these strategies. No? For example, cool roofs, which is relatively easy to do because you can just modify the albedo of the roofs. Cool pavements, you modify the albedo of the streets. So these are easy changes in the parameterizations. But more difficult was to implement the green roofs. So now we have the possibility in BEM to simulate the behavior of green roofs with two types of vegetation. One is grass and one is sedum, and we can also consider the irrigation. So as you know, the green roof, the impact of the green roof will be to change the energy partitioning at the top of the roof, so increasing the latent flux and reducing the sensibility flux. And we also include the possibility to simulate the rooftop solar panels, which are not in principle a strategy to improve the outdoor thermal environments, but the energy produced can be used, for example, to run the air conditioning inside the building. So we can have clean energy to cool the inside of the buildings. And the last development we are implementing in WRF, which is almost ready, is the possibility to estimate some thermal comfort parameters like UTCI in a simplified way, in the sense that since we have we know that the UTCI is strongly dependent on near radiant temperature. So this is affected by the building morphology, the urban morphology. So we introduced the possibility to simulate, for example, to estimate the mean radiant temperature in 3 places for each streets, and so try to account for the variability that we can have in the grid cell of the mean radiant temperature, and so get a distribution of the UTCI. So what can we have with this model? Indeed, we can produce city scale maps of meteorological variables. This is an example of Madrid for maximum and minimum 2 meters air temperature. This is the norm, standard type of output that we can have with the mesoscale model, but we can also produce something more. For example, we can have a map of UTCI, which is what I put on the left. So we can really identify, for example, which are the region of the city we have stronger heat stress, which are not necessarily the regions where we have higher temperatures. And then we can also provide the maps of, for example, of energy consumption using this simplified building energy model. And we can use
I think we need to stop here, but I please ask you to leave that chart, because you can really, the previous one, because you can really lead. If you can please leave it. Yeah, thank you so much. We will use it to moderate the panel. It's a super interesting example. Sorry to interrupt mostly everyone.
I'm sorry to be too long.
It has been, we asked all the panelists to switch on their camera. I have to say that is now if you can leave the previous slide. Yeah, this one. Thanks also to Emily and Rancha who are moderating and bringing us all the set of questions. I would say that this has been a great panel to finish the day. And we are very sorry to interrupt our conversation, but tomorrow also for those that will be able to connect, and this is a message for all the panelists of today, we have a much wider conversation at the end of tomorrow, where perhaps we can have further points and interaction. But coming back to this session, it was very interesting to see in all of your works these links between meteorology, changing meteorology, and a city urban pattern living system that have to be resilient, as very well schematized by heat, but have to be resilient and adaptive to the different happenings, especially heat waves, as displayed here in this latest charts. it's super interesting how in all of your works you're relating meteorology to urban fabric, to the metabolism of the city, to the thermodynamic happenings that are into the city in order to achieve major comfort, as well as to have buildings that are resilient to challenges, as well as in some research to have a system, energy system that are able to adapt to that. So we collect some questions from the public. We go a little bit in random order for this session. Perhaps we start with a question for Nestoras by Emanuela.
Yeah, I have a question related with the tunnel, the air tunnel monitoring. Do you use some kind of standards to assess the monitoring inside the tunnel, or do you have to have standard models or standard limits for validated your monitoring data?
Of course, yes. We have used root mean square error to quantify the agreement, and of course it's not only with it's also the comparison with the two different turbulence modeling approaches. So each one of them was evaluated in terms of wind speed and turbulence intensity in the more than 1200 locations in using the root mean square error.
Sure. Okay. Yes. Perhaps a question of for Gian Domenico, which was about your method. Seems to be super interesting, and actually a question was about the replicability of this methodology in other contexts. The question is related to how is expensive to get to a similar approach for another location, and how long is your process? Yeah.
Okay, yes. From what I've seen right now, for example, for the city of Nicosia in particular, it has been very difficult to retrieve this built environment data because, you know, it's something that needs to be integrated more. So I would say that it depends on the place that on the city of interest, because if this data is available, it will be much more easier. So yes, it depends on the location of the study.
Yeah, and then the last one is for Vaid. No, it's not the last one. The next one is for Vaid from the public. Which method is used to create weather file with extreme events?
Yeah, the method is the one that we have developed ourselves. So it's explained in one paper, but it's using multiple future climate scenarios, using that weather data sets, and then searching for extreme weather data sets to be used in simulations. So I think I don't have time to explain that, but I refer to the paper.
Yeah. Yes, Vaid, you are quite a reference in the field, and one question was you have a very specific publication that target a specific context. Have they been already considered to be implemented by authorities in order to foster, for instance, a better answer to extreme climatic events?
The approach that I have developed has been adopted by this National Research Council in Canada. So I was actually helping them in that, and they have developed these representative weather data sets, and I think they are shared publicly in Canada. So building engineers, for example, they can use that nowadays.
Fantastic, thank you so much. For Alberto, perhaps a final question. It's related to these two maps we are seeing now, but gather our attention, but also someone for the public. Ask if you can perhaps reiterate or explain again how did you get to this sort of heat map that seems to be very useful for planners in order to target their own strategy and perhaps priority of intervention within a city.
Okay, so these are coming from a simulation I did with WRF over Madrid, 1 kilometer resolution. So for every grid point, you can recognize, for example, the shape of Madrid. For every grid point, I have values of this UTCI based, which was estimated based on the air temperature produced by WRF, the air humidity produced by WRF, the mean radiant temperature that I computed, as I explained before, considering the simple morphology of the city, and the wind speed. So how to estimate this mean radiant temperature and wind speed? We have to develop a parameterization accounting for the morphology. So in a certain sense, is a bit long to explain. But the bottom line is that we can produce this map. So this is the maximum value, for example, UTCI. Since I can compute the different values for every grid cell depending on the position of the person where I the point where I compute the mean radiant temperature. Here I just took the minimum value. So in a certain sense is representative of the maximum value of the coolest spot in the grid cell. It's on the left. On the right?
Yes. Unfortunately, we have to close for agreements with build-up. So it's not completely our fault.
Okay.
So, yes,
you can shoot some more questions, Emanuele, if you want. We can have 10 more minutes if you want.
Yes, we have a question. Perhaps we let then Alberto also explain the right map, and then we have a quick question from the public for Vahid, and then we're able to close. Yes.
Okay, the right map is a building energy consumption. So basically, as explained before, in BEM, we can estimate we solve basically an energy budget of the indoor air. So we fix a thermal range of comfort. So when the temperature goes above a certain range, all the extra energy is in a certain sense extracted and ejected to the atmosphere. And from this, we can compute how much energy is needed to do this process. So this is energy consumption. And this depends also on the depth of field.
Thank you, Alberto. And last one for Vahid, the public asks you which kind of programming language do you use in the workflow? Is this based on Python or MATLAB?
I use the MATLAB, but any programming tool that you can handle, it's possible. I mean, it's not depends on what tool you feel okay with or easy with. Yeah.
Okay. I think the main question was also if the source code are available.
No.
Of course. Of course. We understand also that, and I would not share it as well at this point. Then Vahid also has a company where he provides this type of services, so this can also be collaboration with him.
Thanks for mentioning.
Fantastic session. I think it was a wonderful day. Me and Emanuela are very thankful. We want to thank all the panelists as well as Build-Up, Arantxa, and Emily for coordinating all the efforts. So we close the works now, and perhaps we ask Arantxa or Emily if they have any announcement or any comments to add.
Yes, perfect. First thing, Emanuele, thank you so much for choosing Build Up to disseminate this outstanding information. Thank you so much to the speakers. It was long, but we cannot stop hearing you. There was a lot of audience, you will see. Thank you to the audience of Build Up for attending today's session. A reminder that you will be able to find the recordings on Build Up portal on Wednesday. Okay, because Build Up will have a new portal, so it will be in the new portal of Build Up. You're going to be the first ones to be there. And remember that tomorrow we have the second part of this event. We will begin at 10 a.m. I hope that we see a lot of you again there. If you have not registered, remember to register, as there are 2 links different for each event. Is completely separate from today, and we will wish you a very pleasant afternoon. Thank you very much, and goodbye for now.
Thank you, everybody.
Thank you. Bye bye.
Ciao, ciao.
Thank you.
Thank you.